Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest, most beautiful ideas in all of physics, that the universe, in its quiet wisdom, seems to know the best way to do everything, not because it calculates, but because it can't help it. It's built that way. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these calm explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always a joy to see all the places we gather from, each of us drifting through our own small slice of time beneath the same wide sky. Now, feel free to dim the lights, maybe turn on a fan for a soft hum in the background, and let your body settle. Take a slow breath, in and out. Let the weight of the day slide away. We're not racing anywhere tonight. We're just going to drift gently into the story of how the universe decides what to do, and why, even in its smallest details, something strange and wonderful happens when we trust quantum mechanics. Imagine, for a moment, a single beam of light slipping through a window at dawn. It travels silently, painting a stripe of gold across the floor. If that light happens to pass through a glass of water, it bends a little, gracefully, predictably. To our eyes, it's nothing special. But hidden inside that bend is one of nature's most remarkable secrets. The light has found, all on its own, the fastest possible route from air to water to your eye. It behaves as if it somehow knew which way would get there soonest, even though it couldn't possibly stop to think or compare paths. It simply follows a rule written deep into the heart of reality. Always take the path of least time. Scientists call it Fermat's principle, but don't need the name to feel the beauty of it. It's as though every ray of light is a traveller who knows how to move through the world with perfect grace, never rushing, never wasting a step. This quiet efficiency runs deeper than light. Drop a pebble into a pond, and the ripples will spread in perfect circles, each wave choosing the simplest possible shape that still carries energy outward. Watch a cat leap from one windowsill to another. It arcs smoothly through the air, the curve of its body balancing effort and reward without hesitation. Even the planets spinning around the sun seem to be obeying the same ancient whisper. Move in a way that minimizes something precious. To the human eye, this looks like intelligence or design. To physics, it is simply the principle of least action, a law so subtle that it doesn't force anything. It merely describes how things already prefer to move. Action, in physics, isn't the kind of action we usually mean. It isn't drama or force. It's more like a diary, an account of how a system spends its energy over time. You could imagine it as the total effort required for a motion to happen. For each possible way a particle might travel, there's a number that measures how much energy it had, how it changed, and how long the journey took. The universe somehow always chooses the path that makes that number, the action, as small or as balanced as possible. Not zero, not extreme, just right. The path of quiet balance. If we were to peek into the language of mathematics, we'd find that action is built by gently adding up, over time, the difference between two forms of energy, kinetic and potential. But instead of writing it as a formula, you can think of it this way. Imagine a dancer gliding across a stage. Every step costs effort. Every pause stores potential. The dancer moves in a way that keeps this balance almost effortless. That's what the universe does. It choreographs every movement, from planets to photons, to minimize strain. And the outcome is elegance. This idea is ancient, yet endlessly modern. Long before quantum mechanics, physicists like Maupertuis, Euler, and Lagrange noticed that nature behaves as though it were making a quiet bargain between motion and stillness. They called it the least action principle. Later, William Hamilton gave it a more universal form, a way to describe almost any physical system, from a falling apple to an orbiting moon, through this hidden economy of action. What Hamilton discovered wasn't just an equation. It was a kind of music underlying everything that moves. And perhaps what makes it so soothing is that it suggests a universe guided not by brute force, but by grace. Things don't happen because they're pushed. They happen because they follow the simplest possible rhythm. The marble doesn't fall because it's pulled downward. It falls because, in the symphony of all possible motions, the straight drop is the note that resonates most perfectly with the laws of energy and time. When you start to notice this pattern, it's everywhere. A droplet of rain clinging to a leaf forms the smallest surface it can, a perfect sphere. A soap film stretches into the most economical shape possible, spanning its frame with minimal tension. Even in chaos there's thrift. Even in noise there's order. Nature always finds the quietest way to do its work. But of course, this raises a question that once puzzled even the sharpest minds. If light and planets and particles all seem to choose the best path, how do they know what the best path is? Do they somehow test every possibility, every route, every curve, and then pick the right one? That sounds impossible, and yet in a strange way it's almost true. For most of history, scientists assumed that the least action path was something nature simply followed, a rule it obeyed instinctively. But in the 20th century, one man would suggest something far more daring. Maybe, instead of choosing one path, nature tries them all. And the path we see is just where all those possibilities overlap in harmony. As our quiet journey continues, we'll see how that idea led to a new picture of the universe, one where every beam of light, every atom, every heartbeat of matter explores every route it could possibly take, all at once, and somehow the right path emerges on its own. But for now, let's rest in this thought. The universe, in all its complexity, prefers simplicity. It acts not through command, but through quiet balance. It moves the way a breath settles, or a ripple fades, effortless, inevitable, and beautifully calm. Imagine standing on a quiet beach in the late afternoon. The air tastes faintly of salt, and the sea stretches out like a sheet of silver glass. Somewhere out beyond the waves, a swimmer calls for help. Near the lifeguard's tower, someone hears it first. A sharp cry carried on the wind, and a figure begins to run. Sand sprays underfoot. The lifeguard is quick, strong, but the problem is not speed, it's choice. Should they run straight toward the swimmer and dive in early, or should they sprint a longer distance along the shore first, then enter the water later where the swim will be shorter? Running on sand is fast, swimming is slow. The best rescue is a delicate trade-off between the two. This moment, one human, one decision, is the perfect picture of something the universe does constantly. It's a small drama played out not only in lifeguard rescues, but also every time light crosses from air into water. The path that saves a life, and the path that a ray of sunlight takes as it bends through a wave, are governed by the same quiet rule. Both find the route that takes the least time. If you've ever noticed how a straw looks bent inside a glass of lemonade, you've seen the evidence. Light slows down in water, just as a lifeguard slows when swimming. So the ray, in a sense, chooses to dip into the water at an angle that balances two needs: less distance in the slower medium, but not so much that it travels too far through air. The result is a graceful bend that we call refraction. Long ago, the mathematician Pierre de Fermat described this with his principle of least time. He didn't mean that light stops to think, only that when all the possibilities play out, the one that survives in reality is always the path that takes the shortest overall travel time. We could, if we wanted, write this as an equation, but let's stay with the picture instead. Imagine laying transparent strings over the beach, each representing a possible route from the tower to the swimmer. The lifeguard could run straight, or diagonally, or along the shoreline before turning. For every string there's a total time, some moments on sand, some in water. If we tried them all, we'd find one path that makes the stopwatch read the smallest number. That's the one nature uses. In light, this balancing act produces the bending you see whenever sunbeams enter a pool, or a rainbow forms inside falling rain. It's tempting to describe this as cleverness, as though the photon has a plan. But that isn't quite right. Nothing calculates, nothing decides. The world simply behaves in a way that, when viewed afterward, looks astonishingly efficient. It's like tossing 1,000 pebbles into a pond and finding that, by pure interference, the overlapping ripples have arranged themselves into a perfect symmetric pattern. No one organised them. Harmony emerged on its own. The Dutch scientist Willebrod Snell noticed this centuries ago and described the relationship between the angles of entry and exit. Today we call it Snell's law, though we rarely think about the intuition behind it. For Matt's idea, that light's route is the one of least time, explains Snell's discovery naturally. Where the sand meets the sea, so to speak, the angle of bending isn't arbitrary. It's the exact angle that equalises the compromise between distance and speed. The mathematics that expresses this could fill a blackboard, but the essence can fit in an image. The lifeguard diving at just the right point so the swimmer is reached in record time. If we could shrink ourselves down to the scale of photons, we might see something even stranger. Light doesn't follow one path like a single runner, it spreads like an orchestra of possibilities. Every potential route plays its own note, and somehow when the music resolves, only the fastest melody rings out clearly. All the slower routes cancel each other, fading into silence. What remains is the single ray we observe bending through glass. The story feels magical, but it's only nature doing what it always does, letting everything that can happen, happen, and allowing harmony to decide what stays. This is why physicists so often speak of light as both wave and particle. The wave carries the rhythm that determines which roots sing in tune. The particle, the photon, is just what we notice when that wave's harmony becomes focused into one visible spark. It's like hearing only one clear violin above the soft wash of the orchestra. The sound isn't alone. It's simply the part that stands out. When you think of it this way, refraction, the bending of light, stops being a dry fact from high school physics and becomes a whisper from the universe about how it works. Every beam of light, every reflection in a puddle or sparkle on a bottle is a record of nature's quiet efficiency. Nothing is wasted. Nothing is random. It's all time and motion finding their compromise, and there's a comfort in that. When the world feels chaotic, it helps to remember that at the deepest level, even chaos obeys patterns of economy. Waves interfere, particles jitter, but the end result is balance. The ocean doesn't fight the lifeguard. The water and the air simply collaborate in the rescue. Now take one more slow breath and look again at that afternoon beach. The sun is lower now, and the light itself is bending toward you, taking that least time path through air thick with sea mist. The waves move in steady rhythm, like the ticking of a universal clock. Somewhere far off, the lifeguard and the swimmer are only small silhouettes, but in their motions, the run, the dive, the swift line through the surf, you can glimpse the same logic that governs galaxies and atoms. Nature doesn't think, it doesn't plan, it simply acts in the way that costs it the least and achieves the most. As we follow that thought further, we'll begin to see how this simple rule, the least time for light, expands into something far larger. It becomes the least action for everything that moves, planets, pendulums, even the atoms in your own heartbeat. The beach, the swimmer, the bending ray, all are hints of a single pattern written quietly into the universe, a pattern so subtle that we only notice it when we slow down enough to watch the light. If we let the idea guide us onward, we find that the strange grace we saw in the path of light isn't limited to beams and reflections. It's part of a larger pattern, a rule that everything in the universe seems to follow, from pebbles rolling down a hill to planets orbiting a star. And though it sounds grand, the heart of it is simple. Nature always moves in the way that requires the least unnecessary effort. It doesn't need to think. It doesn't even need to know. It simply does what is most natural, and the result is harmony. This rule is known as the principle of least action, though the name can be misleading. Action, in this sense, isn't the kind that fills an adventure movie. It's more like the quiet bookkeeping of motion, a record of how energy changes and flows over time. If you could watch a single grain of sand tumble down a dune, you could describe its journey by tracking how fast it moves, how high or low it is, and how long it takes to get there. Each of these details, speed, height, time, plays a role in the story. Add them all up in just the right way, and you would have a single number that measures the total effort of that path. The principle says that of all the possible ways the sand could roll, the one that actually happens is the one with the least total effort. This idea might sound like a trick of mathematics, but it's more than that. It's a deep expression of how the universe values balance. Where earlier thinkers like Newton described motion in terms of forces, pushes and pulls, the principle of least action tells the same story from a gentler perspective. It says, forget about the shove, look at the grace. The world doesn't move because it's commanded to. It moves because motion, in its quiet economy, finds the path that disturbs, nothing more than necessary. The idea was first whispered in the 1700s by Pierre-Louis Maupertuis, who noticed that nature's behaviour seemed too elegant to be random. He wondered if perhaps there was a kind of cosmic thrift at work, if the universe, in every moment, took the route that minimised what he called action. A few years later, Leonhard Euler gave the idea sharper mathematical form, showing that when you calculate how something moves, this principle naturally falls out of the equations like a signature written at the end of every law. Joseph Louis Lagrange followed, crafting a framework so powerful that physicists still use it today, and William Rowan Hamilton, in the 1800s, polished it into something even more beautiful. A description of nature where time, motion and energy all dance in perfect step, guided by that same principle of least action. But you don't need their names to feel what they discovered. You can sense it every time you watch something fall, glide or swing. A leaf spiralling down through the air isn't calculating, it simply follows the line of least resistance. The same is true of a violin string vibrating after you pluck it. The shape of its motion isn't random, it's the smoothest pattern that satisfies the pull of the string and the stillness of the air. Nature has an astonishing instinct for simplicity. Imagine, if you will, a pianist playing a slow piece in the dark. They don't slam the keys, they don't waste a gesture. Every movement of the hand is small, precise and perfectly timed. The melody flows not because it's forced, but because it's effortless. The universe plays the same way. Every falling apple, every orbiting moon, every swing of a pendulum follows a rhythm that minimizes effort and maximizes grace. That rhythm is action. We might picture it like this. Action is the measure of how much energy experienced something accumulates along its journey. The more wildly it moves, the higher the action. The smoother and more efficient the motion, the less. Nature always finds the sweet spot, where all competing possibilities balance. That's why the planets trace out ellipses, not squares. It's why rivers carve smooth valleys instead of jagged trenches. The world is forever choosing paths that look simple because on some deep level, simplicity is the most stable solution. And perhaps the most magical thing about this idea is how quietly it unites everything. Whether you're describing the flight of a bird or the orbit of Jupiter, the same hidden principle applies. In each case, the world explores countless options, infinitesimal variations of movement, and the one that survives is the one where the total action neither increases nor decreases if you nudge it slightly. It's like walking along a ridge where any small step to the left or right makes you lose your balance. The real path is the one that stays perfectly level. If this sounds mysterious, that's because it is. For centuries, physicists argued over what action really meant. Why the universe would care about such a quantity at all? It doesn't seem like something you could touch or measure directly, yet it appears at the root of everything. Even today, we can't say why nature is written this way, only that it is. What we do know is that from this principle alone, we can derive the equations of motion for planets, pendulums, electric fields, even the flow of heat and sound. In a way, it's as if the universe hides its entire operation inside a single, simple rule. And there's something comforting in that thought too. The same logic that guides a comet across the sky also governs the swing of your arm when you pour a cup of tea. Both follow the least action path, even if we never notice. It's a reminder that the laws of nature aren't separate from us. They're the rhythm we move to, the melody we live inside. If we follow this melody a bit further, we begin to see its quiet mathematics. The least action isn't just the path of least energy. It's the point where the trade between energy and time is in perfect harmony. Imagine a balance scale where motion weighs one side and stillness the other. The universe adjusts itself until the beam stays level. When that balance is reached, the action is least, and the motion feels effortless. The falling apple, the gliding planet, the swing of your heartbeat, they're all solutions to this universal balancing act. And so, when we say nature acts without thinking, we don't mean it's thoughtless. We mean it's perfect in its lack of hesitation. It doesn't need to stop and decide which path to take. It's already on the right one. The principle of least action is, in that sense, the most peaceful law ever written. It tells us that everything, from atoms to galaxies, is already doing exactly what it should, in exactly the simplest way possible. Our gentle exploration now moves ahead. This quiet rule will become even stranger. Because when scientists began to look closer, past the calm paths of planets and falling apples, down into the jittering world of atoms, they discovered that nature's simplicity hides a far more complex truth. Beneath every graceful trajectory lies a sea of possibilities, and the principle of least action, rather than being just a guide, turns out to be a chorus. Every possible path is sung, and somehow only one note reaches our ears. From here, the story opens into something both subtle and beautiful. The quiet mathematics that sits beneath motion itself. It's the language of balance made precise, the way we can translate the grace of a falling leaf or the swing of a pendulum into something the universe seems to whisper in numbers. But we'll stay gentle with the math. There will be no cold symbols tonight, only pictures you can imagine behind your eyelids, like soft chalk lines drawn on a blackboard under starlight. Let's begin with a simple thought. Every movement you've ever seen, an apple dropping from a branch, a wave rolling toward the shore, the moon tracing its arc across the sky, can be imagined as a series of tiny moments stitched together. In each moment, something has energy in motion, which we call kinetic energy, and something held in position, which we call potential energy. Kinetic energy belongs to motion. It's the rush of a rolling ball, the flight of a bird, the spin of a planet. Potential energy is the energy of situation, the stretched bowstring, the lifted weight, the tension that could become motion. The universe is constantly exchanging one for the other, a give and take so seamless it feels almost musical. Now, when physicists talk about the action of something, they mean the grand total of this exchange across time. Imagine keeping a diary of motion, each entry recording for every small instant the difference between energy in motion and energy in storage. Each page of that diary is tiny, almost invisible. But if you add them all together from beginning to end, you get one number that captures the entire story of that motion. How much energy was spent moving versus how much was saved. That number is what we call the action. You don't need to know the formula. You can just think of it as a sum of experiences, the total record of how the universe felt while something moved. Nature, astonishingly, always chooses the path where that diary tells the simplest possible story, the one where any small change would make the balance worse, not better. It's like a tightrope walker keeping perfectly centered. A tiny step to the left or right, and the harmony breaks. The least action path is that perfect middle line where energy and time exchange notes in exact proportion. If you could visualize it, the least action path would look like the calmest thread through a restless sea of possibilities. Imagine you're watching countless faint trails drawn in the air, each representing a different way a ball could fall or a planet could orbit. Most are messy, bending too much, straying too far. But one line glows faintly brighter because it flows in rhythm with the rules of energy and time. That is the true path, the one nature follows. The others are only what might have been. This quiet balance doesn't only explain the fall of apples or the swing of pendulums. It governs the flight of satellites, the stretch of light as it bends near a star, even the subtle tremble of electrons around atoms. In each case, nature doesn't push or pull with intention. It simply allows every possible motion to try itself out. And the one that requires no further correction, the path of minimal disturbance, is the one that unfolds before our eyes. It's as if the universe rehearses every possibility in silence, and only the performance that feels perfectly at ease becomes reality. It's easy to forget that all of this grew out of the simplest of ideas, that nature is economical. We might think of that word as meaning cheap, but here it means something deeper. The universe spends nothing it doesn't have to. It's not stingy, it's precise. It never overshoots, never wastes energy, never rushes. It finds the most direct way to let change happen. That's why so many physical systems, when left alone, tend toward rest or equilibrium. The pendulum eventually stops. The stone settles at the bottom of the hill. It's all the same story, motion finding its calmest form. And when we look closer at this calm, we realize that it has a certain gentleness hidden inside. The mathematics of least action doesn't describe a struggle or a fight. It describes a peace treaty. Every part of the system, every bit of motion and potential comes to an agreement. The energies negotiate until their sum is balanced. And once that happens, everything else follows automatically. Out of this quiet negotiation comes the full machinery of physics, Newton's laws, Maxwell's fields, Einstein's curvature. All of it can be derived from this single principle of balance. What's especially comforting about this is that it shows the universe doesn't need endless instructions. It only needs one rule, whispered softly. Minimize the total effort. From that, all the rich variety of motion, light and matter emerges naturally. It's as if the cosmos is improvising a song with just a single chord, yet managing to play symphonies from it. If we try to capture that feeling, it might sound like this. Action is the melody that connects what could happen with what does happen. It flows through the universe as an invisible rhythm, sometimes loud and sometimes faint, but always present. When you drop a stone into water, the ripples that form are not random. They follow curves that keep the motion smooth and continuous. Each ripple is a slice of the same universal melody. And in that melody lies something deeply human. Our own movements, though guided by muscles and thoughts, also follow this quiet law. You instinctively reach for a cup along a smooth arc, not a jagged one. You walk along paths that minimize strain without thinking about it. Your heartbeat itself finds the most efficient way to pump blood. Without realizing it, your body and the cosmos speak the same language. But what happens when that smoothness is broken? When the motions we thought we understood begin to act strange? When light becomes both particle and wave, and the idea of a single graceful path dissolves into countless possibilities? The early 20th century would bring exactly that kind of shock. The principle of least action would survive, but it would need to learn a new rhythm, one where probability, interference, and uncertainty play the instruments. As we drift into that part of the story, we'll leave behind the calm surface of classical physics and descend into the flickering depths of the quantum world. There, the universe no longer takes one path. It tries them all at once. Yet even in that chaos, the same harmony still whispers underneath. The least action remains, but now it emerges not from simplicity, but from the interference of infinite possibilities, all singing together in time. As the rhythm of our story unfolds, the calm certainty of the classical world begins to tremble. For centuries, scientists believed that nature's laws, as simple and elegant as they were, could explain everything from the flight of a planet to the flicker of a candle flame. But around the dawn of the 20th century, that confidence cracked, not with an explosion, but with a quiet glow. It started with the colour of light itself. Imagine standing in a darkened laboratory late at night while a metal plate heats under a small gas flame. At first it glows deep red, then orange, then white as it gets hotter. It seems simple enough. Hotter means brighter. Brighter means more energy. But when physicists tried to describe this behaviour precisely, using the mathematics they trusted, something broke. The equations predicted that at higher and higher frequencies, toward the bluer, more energetic end of the spectrum, the light should release an infinite amount of energy. An impossible result. The universe, clearly, was not tearing itself apart in blinding blue light. So something was wrong. That quiet crisis came to be known as the ultraviolet catastrophe, and it haunted the minds of physicists at the turn of the century. For years they had treated light as a smooth wave, spreading endlessly like ripples on a pond. Waves made sense. Waves were continuous and predictable. But nature was giving them a hint that it wasn't quite that simple. The glow from a hot object followed a pattern, but one that the old theory couldn't explain. It was as though the music of light had missing notes, places where the expected melody refused to play. Enter Max Planck, a German physicist with a thoughtful face and a habit of working late. In 1900, in an act of both desperation and insight, he tried something radical. Instead of assuming that light's energy could take on any value, he proposed that it could only be released or absorbed in specific tiny packets. He called each packet a quantum of energy. The size of each packet was determined by two things: the rhythm of the light and a new universal constant he named h, a number unimaginably small but fundamental. The higher the rhythm, the faster the vibration of the light wave, the larger the packet of energy. In simple terms, energy came in rhythm-sized chunks. Each beat of the light carried its own distinct pulse. When Planck applied this idea, the impossible infinities vanished. The spectrum of glowing light now curved and faded exactly as nature showed it should. His little constant, he, fit perfectly. He had solved the puzzle, though he admitted he didn't quite believe his own theory. It felt like a trick, a mathematical convenience. Surely light was still a wave, smooth and continuous. The idea that it could come in indivisible packets seemed absurd. And yet, as Planck himself wrote later, an act of desperation had opened the first door into the quantum world. You could imagine it like this. For centuries, scientists had believed that the universe played music on a continuous violin string, capable of sliding smoothly from one note to the next. Planck's insight revealed that the instrument was actually a harp, plucking distinct tiny notes one at a time. Between each note, there was silence. The melody of the universe wasn't continuous. It was made of discrete beats. Nature, it turned out, kept rhythm. To visualize what Planck found, imagine painting a rainbow by hand. In the classical picture, you could choose any shade you liked, an infinite spread of colors blending seamlessly. But in the quantum picture, nature has a limited palette, a finite set of precise hues. You can mix them to create something that looks smooth, but beneath the surface, each colour is made of individual strokes, indivisible and whole. This may sound like a small change, a tweak in how we think about light, but it was revolutionary. It suggested that energy itself might be quantized, chopped into tiny indivisible packets. Every time you switch on a lamp, every time sunlight warms your skin, you are being touched not by a continuous wave, but by countless single quanta, each carrying just enough energy to keep the world bright and warm. And that constant H, Planck's constant, became the heartbeat of the microscopic universe. It's the measure of how grainy reality is. You could think of it as the smallest tick of nature's internal clock, the limit below which smoothness dissolves into steps. If it were larger, the world would shimmer and jitter in visible ways, uncertainty bleeding into everyday life. If it were smaller, the quantum world would hide even deeper beneath the surface. But at the value it has, tiny but not zero, it makes the world we know possible, classical at large scales, but quietly quantized underneath. Planck didn't know it yet, but his discovery would start a revolution. Within just a few years, others would follow the thread he had tugged on. Einstein would use these same quanta to explain how light could knock electrons out of metal, revealing that light behaves not just as a wave but as a kind of particle, a packet of energy with both rhythm and punch. Bohr would later use the same idea to explain why atoms glow in colours so specific they can be used like fingerprints. One by one, the old continuous universe began to crumble, replaced by something granular, rhythmic, and deeply mysterious. When you think about it, this shift in understanding mirrors the human experience. We too often imagine our lives as smooth lines, continuous stories, unbroken flows of cause and effect. But reality tends to move in steps. Our days come in moments, our choices in pulses, our emotions in bursts of energy and rest. Planck's discovery was a reminder that even at the smallest level, the universe works not as an endless stream but as a series of notes. And somehow, when played together, those notes form the symphony of everything. So on that quiet night in 1900, when the spectrum of glowing metal finally made sense, the world changed. A small constant, barely measurable, had rewritten the rules of reality. The classical light of Newton and Maxwell was no longer the whole truth. A new, flickering universe had begun to emerge, one where certainty would fade and possibility would take its place. As we drift further into this story, we'll see how the next thinkers, Einstein, Bohr and others, would take Planck's tiny, trembling idea and build from it an entire new picture of existence. A picture where light and matter trade places, particles behave like waves, and the solid world reveals itself as a shimmering field of probabilities. For now, though, it's enough to remember this. Every spark you've ever seen, every colour you've ever admired, is the echo of a deeper rhythm. A rhythm that began the night the spectrum broke, and the universe learned to play in quanta. If we follow the glow of Planck's discovery just a little further, we find another light waiting there, one that flickers between mystery and revelation. Planck had shown that energy might come in little packets, each one tied to the rhythm of the light. But in 1905, a young patent clerk named Albert Einstein took that idea and dared to believe it was real. To him, these packets weren't just mathematical tricks or abstract conveniences. They were tangible, physical things. Light, he said, wasn't just a wave. It could also behave like a shower of particles, each one a single tiny pulse of energy. At the time, that suggestion was almost scandalous. For centuries, light had been the model of continuity. Isaac Newton had once described it as a rain of particles, yes, but that view had long since given way to the beauty of waves, the gentle spreading ripples that explained colour interference and reflection. The wave theory was elegant, and it worked. Yet experiments on metal surfaces were hinting that something deeper was happening. Physicists had noticed that when they shone light on certain metals, electrons would leap out, as if jolted awake. This was called the photoelectric effect. The mystery was that the brightness of the light didn't seem to matter much. What mattered was its colour, its frequency, its rhythm. Red light, no matter how bright, wouldn't kick out electrons at all, but blue light, even faint blue light, could. The pattern made no sense if light were simply a wave. Waves spread their energy smoothly. They should work eventually if you waited long enough. But the electrons refused to budge unless the light's rhythm was fast enough. It was as though each electron demanded a certain price to be freed, and only light with the right beat could pay it. Einstein proposed a daring explanation. What if each little packet of light, each quantum, carried a specific amount of energy, proportional to its rhythm? The faster the rhythm, the greater the energy. In soft language, he said, each light particle's energy equals a constant times its vibration rate. That constant was Planck's h, the same tiny number that had rescued physics from its spectral disaster. Now it had become something even more profound, a kind of currency exchange between light and matter. Einstein's insight changed everything. When light struck the metal, it wasn't a smooth wave washing over the electrons. It was a rain of tiny bullets, each carrying just enough energy to knock one loose. Red light's bullets were too weak, no matter how many came. Blue lights were few, but powerful, and so the electrons jumped. The photoelectric effect, once a puzzle, became a doorway to understanding that light is both wave and particle, an infinite ripple that can also arrive as a discrete beat. Years later, this discovery would win Einstein the Nobel Prize, though not for relativity as many assume, but for this simple, radical idea that light itself has a dual nature, dancing between continuity and discreteness, between wave and particle, between the visible and the unseen. While Einstein was giving light its particle side, another physicist, Niels Bohr, was looking inward, into the atom itself. He too found something extraordinary. At the heart of every atom lies a tiny, dense nucleus surrounded by electrons. According to classical physics, those electrons should spiral inward and crash into the nucleus almost instantly, radiating energy as they go. But they don't. They stay suspended in space, orbiting like planets that never fall. The question was, why? Bohr borrowed Planck's idea of quantization and took it one step further. He suggested that electrons could only orbit the nucleus in specific allowed paths, each one tied to a precise level of energy. When an electron jumps from one orbit to another, it absorbs or releases a packet of light exactly equal to the difference between those two energy levels. It was as if the atom itself were a miniature staircase. Electrons could stand only on the steps, never in between. He described these orbits using whole number multiples of Planck's constant, divided by a circular measure called 2 pi, the same number that defines the geometry of circles. You don't need the formula to understand it. Think of it this way. Each allowed orbit fits an exact number of standing waves, like loops on a vibrating guitar string. The waves that don't fit cancel themselves out, fading away. Only the harmonies that fit perfectly survive. The atom, it turned out, was a kind of instrument, playing only certain notes. That was why hydrogen, the simplest atom, glowed in distinct colours when excited. Each colour represented an electron jumping between levels, emitting light of just the right energy. No more, no less. The universe wasn't painting with a continuous brush anymore. It was playing chords, one note at a time. It's worth pausing here to notice how extraordinary this shift was. The same idea, tiny quanta of energy, had now appeared in two completely different realms. Planck had used it to explain glowing heat. Einstein had used it to explain light's interaction with matter. Bohr now used it to explain the structure of atoms. What had begun as a mathematical fix was starting to look like the language of nature itself. And yet, these discoveries didn't destroy the old picture of waves and smoothness, they deepened it. Light was still a wave, but it could also act as a particle. Electrons were still particles, but they moved as though guided by invisible waves. Everything that once seemed solid was starting to shimmer. The universe was no longer made of matter alone. It was made of patterns, of vibrations, resonances, and rhythms, each quantized, each following rules that felt almost musical. It was as if the universe had always been a grand symphony, but for the first time, we could hear the individual instruments playing beneath the harmony. The large-scale music of planets and pendulums was still there, smooth and flowing. But now underneath there was a quieter, granular rhythm, a lattice of notes too small to see but impossible to ignore. To Bohr, this was not chaos, but beauty. His model explained the colours of the stars, the chemistry of the elements, the way matter interacted with light. The world, once thought smooth, was built from steps. Each step was precise, distinct, necessary. And even though the model would later be refined and replaced, the idea that energy comes in discrete levels, like rungs on a ladder or loops on a vibrating string, would remain one of the deepest truths in science. As we drift deeper into the quantum dawn, we begin to sense a pattern emerging. Planck's quanta of energy, Einstein's photons of light, Bohr's quantized orbits, all point toward a strange unity. Matter and energy are not opposites. They are two versions of the same thing, rhythm frozen into form, or motion released as light. And if the smallest pieces of the world move by rhythm and harmony, what happens when their waves overlap? What happens when the universe allows not just two paths, but infinitely many, all playing at once? That's where the story next leads, a place where even possibility itself becomes the instrument. From here, the story opens into something even stranger. By now, the old picture of the universe, solid, predictable, clockwork, has been replaced by something shimmering. Light can act like particles, and particles can hum like waves. It was only a matter of time before someone wondered whether that duality might run even deeper. What if this symmetry between matter and light wasn't just coincidence? What if everything in the universe was built from the same kind of wave-like rhythm, just arranged in different keys? That question belonged to a quiet, thoughtful Frenchman named Louis de Broglie. In 1924, while still a graduate student, he proposed something audacious. If light, once thought to be only a wave, can behave like a particle, then perhaps particles, like electrons or atoms, can behave like waves. It was a breathtaking inversion, as if he had turned the entire logic of physics inside out. Where others saw contradiction, de Broglie saw symmetry. He imagined that every bit of matter carries within it a tiny invisible wave, with its own rhythm and wavelength. The faster the particle moves, the shorter its accompanying wave. The slower it moves, the longer the wave stretches out. He described the relationship softly as momentum and rhythm are twins. The more you have of one, the less of the other. It was a poetic idea, but also a precise one. He didn't picture the wave as something separate from the particle. They were two faces of the same coin. The wave guided the particle, and the particle gave the wave a place to exist. In the spaces where the wave resonated perfectly, where it fit into itself an exact number of times, looping smoothly like a closed melody, the particle could stay. Everywhere else, its wave would cancel itself out. What remained were only certain orbits, certain energies, certain harmonies. And with that, Bohr's arbitrary ladder of atomic levels suddenly made sense. They weren't random rules at all. They were the natural result of a wave fitting neatly into the architecture of the atom. To imagine it, picture a circular pond, perfectly still. Drop a pebble in, and ripples spread outward, reflecting off the edges and overlapping. In most cases, they cancel each other in tangled chaos. But sometimes, for certain wavelengths, the ripples line up with themselves, crest meeting crest, trough meeting trough, forming a stable pattern that seems frozen in place. That's a standing wave, motion and stillness combined. De Broglie realised that the electrons orbiting a nucleus behave exactly that way. Their waves fold perfectly into loops, locking into stable shapes that can persist. Each allowed orbit corresponds to one of these standing patterns, with an exact number of wave loops fitting around the atom's circumference. Not one more, not one less. The mathematics was simple but revolutionary. It implied that all matter, every grain of dust, every drop of rain, even you, has a wavelength, though far too small to notice in everyday life. For an electron, the wave is large enough to shape its world. For a person, it's smaller than an atom, impossible to sense. But in principle, the same rule applies. The universe is not built of billiard balls, but of vibrating possibilities. Even the things that seem perfectly still are humming quietly at their own frequency. When de Broglie shared his idea, many of his elders smiled politely but doubted him. It was too radical, too strange. But a few years later, in 1927, experiments proved him right. At Bell Labs, scientists fired electrons through a thin sheet of crystal and found that they scattered not like tiny pellets, but like waves. The pattern they formed was identical to the diffraction patterns made by light. The electrons interfered with themselves, creating rings of brightness and darkness. The implication was inescapable. Matter is not only substance, it is also wave. The effect was subtle but profound. It meant that everything, every atom, every speck of dust, every heartbeat, is both particle and wave at once. We never notice this duality in our daily world because for large things, the wave part is unimaginably small. The wavelengths shrink to near nothing, so we see only the particle side, the chair, the cup, the hand resting upon it. But in the quiet realm of the very small, the wave nature dominates. There, matter behaves more like music than machinery. Interference, resonance, harmony. These become the real rules. And so the language of physics began to shift. Scientists no longer spoke only of trajectories or forces. They spoke of amplitudes and phases, of patterns that reinforced or cancelled, of probabilities that flowed like ripples in a pond. In this new view, motion was no longer the march of solid things, but the unfolding of waves in a sea of possibilities. The old laws of least action were still true, but their meaning had deepened. The universe was no longer choosing one path, it was exploring them all, letting interference decide which ones would remain visible. To grasp the beauty of that, imagine walking through a forest where paths fork endlessly. Instead of taking one route, you somehow step into all of them at once. Some routes circle back, some wander off into silence. As you move, the steps that match rhythm with the landscape reinforce each other, becoming clearer, while the mismatched ones fade. By the time you reach the clearing, all the wrong turns have cancelled out, and only one gentle path remains, the one you actually see under your feet. That's what the quantum world does. It explores everything, everywhere, all at once, and what we call reality is simply the melody that survives. This new understanding didn't destroy classical physics, it completed it. The smooth arcs of planets, the elegance of least action, the whisper of symmetry, they all still hold true, but now we see why. The classical world is what emerges when the countless quantum waves underneath interfere perfectly, cancelling their differences until only one clear note remains. What we call cause and effect, what we call certainty, is simply the harmony left after infinite possibilities play themselves out. For de Broglie, this realization was both scientific and spiritual. He once wrote that the history of the universe is a vast symphony of waves, And if you listen closely, you can almost feel it. The hum of matter, the rhythm of light, the silence between the notes. It's a comforting thought. The same physics that shapes galaxies also sings in the quiet spin of an electron. As our quiet journey continues, we'll see what happens when those waves meet not just two possible paths, but countless ones. When the universe allows every possible route to exist simultaneously, and the final reality emerges only through their interference. That's where the path integral story begins, where a man named Feynman would take this quiet wave symphony and turn it into a vision of infinite possibilities, each one real, each one contributing to the world we see. Our gentle exploration now moves ahead. The quiet rhythm of de Broglie's waves begins to merge with the light's own shimmering mystery. The year is 1927, and the laboratory has gone dark except for a small, single source of light. In front of it stands a metal plate with two thin openings, two slits so close together that they look like a pair of eyelashes. Behind that plate, a screen waits to record where the light lands. It's one of the simplest experiments ever built, and yet it holds within it the strangest truth ever uncovered. When light passes through a single slit, it behaves much like you'd expect, forming a bright spot on the screen behind it. But when the second slit is opened, something magical happens. Instead of two bright spots, the screen fills with a pattern of alternating light and darkness, like ripples from two pebbles tossed into a pond. Bright lines where the ripples meet and sink, dark lines where they cancel each other out. This is the fingerprint of a wave, interference. The waves of light spread from both slits, overlap, and weave together into a pattern of harmony and silence. For centuries, this was accepted as proof that light is a wave. But then came the twist. When the experiment was repeated with particles, electrons, fired one by one through the same two slits, the same pattern appeared. Even though each electron hit the screen as a single point, over time the points built up into an interference pattern, exactly like the light. It was as if each electron had passed through both slits at once, interfering with itself. Matter, it seemed, wasn't choosing a single route. It was exploring all routes at once. The most unsettling part was what happened when scientists tried to watch more closely. If they placed a tiny detector at the slits to see which one the electron went through, the interference vanished. The electrons suddenly behaved like tiny bullets again, forming two simple clusters. The mere act of observation changed the outcome. Looking somehow collapsed the shimmering wave of possibilities into a single, definite event. Reality, it seemed, only decided what it was when it was being looked at. We can describe the mathematics of this in elaborate ways, talk about amplitudes, probabilities, and superposition, but perhaps it's better to stay with the image. Imagine a traveller standing before two open doors, each leading to a different path through a forest. In the quantum world, the traveller doesn't choose one door. They drift like mist, flowing through both, exploring every branch of the forest simultaneously. By the time they emerge at the other side, all the overlapping routes have interfered with one another. Some strengthen, some cancel. The path that remains, the one we actually see, is the quiet residue of all those possibilities interacting. That is the world we live in, the sum of every might have been, softly averaged into being. The experiment seems simple, but its implications are dizzying. It tells us that the universe is fundamentally built on probabilities, not certainties. Every particle, every photon, every electron lives as a wave of potential until an interaction, an observation, causes it to take on one outcome. The world is not solid until it participates in its own measurement. It's not that reality hides, it's that it waits to be asked which of its possibilities it wants to become. This isn't mysticism, it's the purest, most testable physics we have. The double-slit experiment has been repeated countless times, with light, with electrons, even with large molecules made of hundreds of atoms, and every time the pattern of interference appears. Every time the world reminds us that matter, at its root, is a symphony of maybes. The familiar solidity of things, your desk, your hand, the pen you hold, is simply the harmony that emerges after countless tiny waves have cancelled each other's discord. Reality is what remains when all the possibilities have finished interfering. Even Richard Feynman years later would call this the heart of quantum mechanics, the one experiment that contains the whole mystery. He famously said that no one truly understands it, and yet it works with perfect precision. From it, we can predict the behaviour of transistors, lasers, atoms, and stars. Every technological marvel of the modern world traces back to this shimmering interference pattern, first glimpsed in a dark lab nearly a century ago. It's tempting to think of the double slit as an experiment about particles, but really it's an experiment about us, about what it means to know something. When we don't look, the universe behaves as though it's trying every path. When we do, it seems to choose. But perhaps both pictures are true, and neither is complete. Perhaps the act of seeing isn't a disruption at all, but a joining. The universe observing itself through us. Imagine, for a moment, watching moonlight through the blinds of a window. The beams overlap, cross and shimmer, forming faint patterns on the wall. That pattern isn't something the light decides on in advance. It's something that emerges as the waves meet. In the same way, reality isn't pre-written. It unfolds where possibilities meet and merge. The light and the shadow on the wall exist together, each defining the other, each revealing the pattern's shape. The double-slit experiment shows that the universe paints itself this way, stroke by stroke, probability by probability, until the picture resolves into the world we know. And yet, there's a serenity in that uncertainty. It means the world is still creative, still fluid, still alive with unseen choices. It means that beneath every object and event lies an ocean of potential, quietly collapsing into the moment you experience. The surface of reality may seem solid, but it rests on a foundation of shimmering interference, a cosmic music that never stops playing. As we drift further into this strange harmony, the next part of our journey will take us into the mind of the man who turned this mystery into a principle, the man who decided to stop asking which path nature takes, and instead accept that it takes them all. Richard Feynman would call it the sum over histories, a way of seeing that unites every possible journey into one coherent picture. To understand how, we'll have to trust quantum mechanics completely, and let the universe show us what happens when we stop demanding a single story. It's late evening at Princeton, sometime in the 1940s. The corridors of the physics department are almost empty now, echoing faintly with the tap of distant shoes and the occasional creak of an old radiator. A single light remains on in one of the offices. Inside, a young man paces the floor, sleeves rolled up, a piece of chalk twirling endlessly between his fingers. His name is Richard Feynman. He's restless, brilliant, and just a little impatient with the ordinary ways of thinking. He's been staring at an idea that refuses to fit neatly into any equation he knows. Quantum mechanics works. It predicts experiments with incredible precision, but its machinery feels too rigid to him, too fragmented. He wants to see the whole picture, the elegant simplicity hiding underneath. And as he walks, he begins to imagine something strange. What if, instead of trying to calculate what a particle does step by step, we imagine all the ways it could possibly move, every path it could take, every twist and turn, every hesitation and detour? Maybe the truth isn't that nature chooses one path, but that it explores them all. It's an idea as simple as it is impossible. If you could follow a single particle from one point to another, you might expect it to travel in a straight line, like a pebble tossed through the air. But Feynman imagined something different. In his mind, the particle doesn't take one route, it takes every route. The short way, the long way, the looping, zigzagging, wildly impractical ways. Every possible journey the particle could make, it makes them all. And then somehow the universe adds them together. Each path contributes a tiny whisper, a little wave of possibility, and when those waves overlap, they interfere with one another. Some strengthen, some cancel. What remains after all that interference, the faint pattern left behind, is what we actually see in the world. The straight line, the predictable trajectory, the simple cause and effect. All of it is just the visible surface of something much deeper. Reality, Feynman realized, is the interference pattern of infinite possibilities. He called this picture the sum over histories, not in the sense of adding numbers, but of adding stories, the total collection of all the ways something could happen. To find what truly occurs, nature doesn't pick the best path by command. It simply lets all paths contribute, and harmony chooses for it. The smooth classical motion we see in the macroscopic world is simply the melody that survives after the infinite orchestra of paths has finished playing. To imagine what that looks like, think of standing on a cliff and watching waves roll toward the shore from far away. Each wavelet has its own rhythm, its own direction, but as they overlap, some parts grow stronger while others fade into stillness. The beach receives not one wave, but the sum of all their interference. The water you see rushing up to your feet is just the collective decision of countless ripples meeting and agreeing on a direction. That's what Feynman saw when he thought about particles. They weren't marching soldiers obeying orders. They were waves of probability, all moving, overlapping, cancelling and adding until the calm result emerged. He loved the strangeness of it. He didn't try to make it sound less weird or more comfortable. He simply trusted it. His method didn't just describe light or electrons. It described everything that moves, from photons to planets. Every action in the universe could be thought of as the sum of all its possible paths, each one contributing its own small piece of the story. The mathematics behind this would later be written in elegant shorthand. It would say, take the exponential of the action divided by a tiny constant and sum over all paths. But those words, and even the equation they suggest, don't capture the poetry of it. You can imagine it more softly. Every path paints a faint colour across the canvas of the universe, its hue determined by the rhythm of its motion, the action. The brightness of each colour fades and shifts, depending on how the path aligns with its neighbours. When all the colours overlap, only certain shades survive. The final picture, what we call reality, is the luminous pattern that remains. Feynman's insight was more than a new technique, it was a change in perspective. For centuries, physicists had tried to find the single correct path, the one solution that satisfied nature's laws. Feynman suggested that there is no single path, only the harmony of all of them. The world isn't a machine choosing options. It's a symphony playing every possibility at once, with interference shaping what we hear. To him, this was not just beautiful. It was natural. It explained why light takes the path of least time and why planets follow the path of least action. In his formulation, those least paths weren't chosen. They simply emerged. All the other possible paths still exist, but their rhythms cancel each other. The least action path is the one where everything aligns, where the phases hum in tune. Nature's perfection isn't in calculation, it's in resonance. You could imagine this too as a vast network of threads stretched between 2 points in space. Each thread represents a path the particle could take, and each vibrates with its own frequency. When you pluck them all together, they produce a shimmering pattern of sound and silence. Most of the threads cancel one another, their vibrations clashing in chaos, but some align perfectly, creating a clear tone that rises above the noise. That tone is the reality we experience, the path that feels solid, the outcome that seems inevitable. The rest still exist, but they hum below our perception, quiet and unobserved. As strange as it was, Feynman's way of thinking worked. When he tested it against the quantum rules we already knew, it gave the same answers, but with a simplicity and elegance that made physicists gasp. Problems that had once required pages of dense equations could now be seen as simple geometries of possibility, woven together by interference. It was as if he had found a way to let the universe do its own bookkeeping. Yet what made Feynman's vision most remarkable wasn't just the science, it was the humility in it. He wasn't saying that he understood everything, he was saying that we don't have to. We can trust the universe to handle its own infinite sums. Our job is only to listen, to observe the melody that results. In that sense, his approach wasn't just mathematics, it was meditation. And so, as he paced that Princeton office, sketching paths in chalk and waving his hands through the air, he was doing more than physics. He was learning to see the world as it truly is, not a sequence of events, but a flowing tapestry of possibilities. Every step, every turn, every flicker of light is part of a grand interference pattern that gives rise to the world we know. When you understand that, even briefly, it changes how you see everything. The way water glints, the way sound echoes, even the way thought unfolds. As we drift further into the story, we'll explore how this interference works more deeply, how the universe decides which possibilities vanish into silence and which sing into existence. It has to do with rhythm, with alignment, and with a constant so small it almost disappears, a whisper of a number that measures how sensitive the world is to its own harmonies. But before we get there, imagine Feynman one last time in that quiet hallway, chalk in hand, tracing invisible paths through the air. Every line he draws, every idea he tries, contributes to the infinite sum, and somewhere in that sum, the shape of the universe waits to be revealed. If we follow the thread of Feynman's idea a little further, the picture begins to shimmer in detail. The particle no longer feels like a solid bead racing along a fixed line. It becomes something softer, an accumulation of rhythms, 1,000 quiet waves overlapping, each one carrying its own whisper of possibility. The miracle of Feynman's approach wasn't that he added new mathematics, it was that he gave the mathematics a heartbeat. Every possible path, he said, carries its own rhythm, its own phase, and together these rhythms compose the world. To see how it works, imagine a circle drawn in the air, glowing faintly. At its edge, a tiny arrow spins, like the hand of a clock. That arrow represents the phase of a single path, the rhythm of its contribution. For each route the particle might take, the arrow points in a slightly different direction, turning faster or slower, depending on the action of that path, the story of its energy and time. If two paths have nearly the same action, their arrows point almost the same way, and when added together, they reinforce each other. But if their actions differ greatly, their arrows spin out of sync, and their contributions cancel, fading into silence. In the deep language of physics, this spinning rhythm is sometimes written as the exponential of I times the action divided by a constant. But we can think of it more gently. Each path is like a musician playing a single note. The pitch of that note depends on how the universe felt along that path, how much energy it carried, how long it took, how it moved through space and time. The tiny constant called h-bar, a whisper small number derived from Planck's constant, sets the scale for how fast the notes spin. When the notes fall out of tune with one another, their sound dissolves into quiet. When they align, they sing. This is what Feynman realized, that the classical world, the predictable world of falling apples and orbiting planets, isn't separate from the quantum world. It's what happens when all those spinning arrows average out. In the quantum sea, every path is tried, every note played, but in most cases their phases clash, cancelling almost perfectly. Only the paths whose rhythms are most in harmony, those near the stationary action, survive. They reinforce each other, creating a single, steady melody. That melody is what we see as the classical path, the trajectory of least action, the one that seems to make perfect sense. You could imagine it like standing in the middle of a vast orchestra, blindfolded. Every musician is playing their own line, violins, flutes, horns, drums, each slightly out of step. At first, it sounds chaotic. But then, as the notes blend and cancel, you begin to hear a faint pattern rising out of the noise, one clear, resonant chord. That chord is the path the universe takes. It isn't chosen in advance. It simply emerges from the sum of all the music underneath. This idea, though almost mystical in its beauty, is practical to the core. It explains how the classical world emerges naturally from the quantum one, without any need for hidden switches or special rules. The laws of motion, the principles of least time and least action, all of them arise because the universe, in performing its grand interference, leaves only the harmonized paths visible. Reality, in other words, is the leftover music after every possible tune has been played. Let's try to picture it another way. Imagine tossing a handful of small sticks onto a table, each one with an arrow drawn along its length. They fall in random directions, some pointing north, some south, some sideways. If you look at them all together, they nearly cancel. Their directions average to 0. That's what happens with most quantum paths. Their contributions nullify each other because their rhythms don't align. But near the least action path, the arrows begin to point almost the same way. There, their strengths combine. A clear direction appears. That is the path nature follows. The strange constant h-bar determines how forgiving this process is. It's a measure of how easily the arrows lose sync. If h-bar were large, many paths would stay coherent. The world would shimmer with competing possibilities, never quite settling into one. But because it is so tiny, so unimaginably small, only the narrow band of nearly perfect harmony survives. That's why the macroscopic world feels solid and deterministic. The cacophony beneath it is real, but the noise has mostly cancelled itself away. It's humbling, isn't it? The familiar solidity of a stone, the regularity of a pendulum, the simple arc of a ball through the air. These are not things that exist because the universe is simple, but because it is infinitely complex. Every moment of certainty we experience is the quiet residue of infinite uncertainty. We walk, speak, and breathe on the smooth surface of what's left after all the possibilities have interfered. Feynman once described this with characteristic clarity. He said that in quantum mechanics, a particle going from one point to another is like light reflecting off a mirror. Light doesn't choose the shortest path, it explores every path, and the ones near the shortest all reinforce one another. The same thing happens with matter. The paths that differ wildly from the classical one cancel out because their phases spin too quickly. The ones close to harmony add up. The result is the same as the principle of least action. The ancient idea that nature seeks simplicity wasn't wrong. It was simply an echo of quantum interference, magnified to human scale. And in this echo, we find something deeply peaceful. The universe doesn't need to be commanded, it doesn't need to make choices or exert will. It just hums, and from that hum, order appears. Each path, each vibration, each possible world contributes its part to the grand interference. Even the paths that cancel aren't wasted. They're the silence that allows the melody to exist. So when we watch a beam of light curve through glass, or an apple fall, or a planet trace its orbit, what we're seeing is the harmony left after the infinite symphony is quieted. The quiet isn't absence, it's resolution. A cosmic agreement among infinite rhythms that results in a single, visible world. And maybe that's why reality feels so calm, so steady, compared to the restless potential underneath. It isn't that the chaos is gone, it's that it has found its balance. As we drift a little deeper into the story, this balance will reveal its full grace. We'll see how the stationary paths, the ones that survive the interference, build the world of cause and effect we know so well. They are not separate from the quantum ocean. They are its cresting waves. And we'll see that the line between the quantum and the classical isn't a wall. It's a song, fading from infinite voices to one clear tone. When the phases collide and worlds go quiet, the melody that remains is the one we live inside. If we follow the path of Feynman's idea just a little further, we reach a moment of clarity, a point where the noise of infinite possibility begins to resolve into the steady rhythm of the world we know. The quantum sea, filled with endlessly spinning arrows and whispering waves, doesn't vanish. It simply quiets down. Out of that quiet, the familiar, predictable world reappears as if rising from fog. It's here, in the stillness after interference, that the classical universe is born. Imagine for a moment standing inside a clock shop after hours. Hundreds of pendulums swing at once, each clock ticking in its own rhythm, slightly faster or slower than its neighbours. At first, the sound is chaos, 1,000 mismatched ticks clattering against one another. But if you wait long enough, the air itself begins to carry vibrations between them. Slowly, through the invisible connection of sound, the pendulums start to synchronize. One by one, the rhythms align. The noise dissolves into a single heartbeat of motion. That's what happens inside the quantum world. Every possible path, every trembling arrow, every potential history adds its voice to the mix. Most clash and cancel out, but a few stay in tune. Those few, the ones in perfect rhythm, form the steady beat of classical reality. In the language of physics, we'd call this the stationary phase approximation, the idea that among all the possible ways something might move, the ones that matter most are those where the rhythm, the phase, changes least. But we don't need the equation to feel what that means. It's like walking along a ridge high above a valley. On either side, the slope falls away sharply, but at the ridge's centre, every small step left or right feels balanced. That balanced crest is the classical path, the one the universe settles on, not because it chooses it, but because all the nearby possibilities cancel each other out. The rest falls silent. It's an astonishing thought that everything solid, certain and predictable in our world, the arc of a thrown ball, the orbit of the moon, the swing of a pendulum, emerges naturally from the interference of infinite uncertainty. Determinism isn't the opposite of chaos. It's what remains when chaos finishes its song. The universe doesn't eliminate the alternatives, it averages them. What we call the laws of motion are simply the points where the symphony of possibility resolves into a single note. You can picture it like this. Imagine you're looking down at a still pond after a storm. Countless ripples overlap, intersecting at every angle. The surface seems wild, unpredictable. But if you stand back, certain patterns emerge. Areas where the water almost stops moving, where the waves cancel into calm. Those calm regions are the classical trajectories, the paths of least action. The ripples don't disappear. They've simply balanced themselves so perfectly that the water appears still. In a sense, the principle of least action was never a mystery at all. It was the language of interference, spoken long before we understood it. When we say nature minimizes action, we're really saying that the phases of all possible paths align most closely there, leaving behind a single surviving melody. The straight line of a falling object isn't chosen by a force. It's the resonance left after infinite possible curves have argued themselves into agreement. And this doesn't just happen in simple systems. Every object around you, from a drifting dust mote to the orbiting planets, is the sum of interference among countless invisible possibilities. The fact that they move predictably, that they obey what we call laws, is not a mark of simplicity, but of enormous underlying complexity. The classical world is not the absence of the quantum. It's the quantum world seen through the lens of overwhelming harmony. This perspective changes the way we think about cause and effect. We often picture the world as a chain of events, each one pushing the next like dominoes falling. But in Feynman's picture, Cause and effect emerge from interference, not impact. The universe doesn't push itself forward step by step. It resonates forward, like music continuing from one chord to the next. The rhythm carries information about what came before and what's likely to follow, not through force, but through coherence. When you drop a ball and it falls predictably, that's not because gravity commands it. It's because all the wildly different ways the ball could have fallen cancel one another, leaving only the one smooth descent we see. There's something deeply peaceful in that idea, isn't there? The realization that order isn't enforced, it's revealed. The world's steadiness isn't the product of strict control, but of harmony naturally reached. Every predictable motion is a meditation that the universe performs on itself. It tries everything, explores every possibility, and then, through interference, finds balance. And yet that balance is never absolute. Even as the macroscopic world appears calm, the quantum noise continues underneath, forever whispering. The particles in your body still explore their endless paths. They just do so in synchrony, their tiny differences averaging out. Every solid object is a choir of quantum voices so perfectly tuned that it sounds like a single tone. We call that tone reality. This understanding reshapes even our sense of beauty. We often admire simplicity, the elegance of a law, the symmetry of a curve, the stillness of equilibrium. But beneath every simple form is an ocean of complexity, cancelling itself into clarity. A straight beam of light, a perfect circle, a steady rhythm. These are not signs of emptiness. They're signs of perfect interference, of everything fitting together so precisely that all the discord vanishes. Simplicity is not the absence of detail, it's the triumph of balance. Feynman once said that if you truly wanted to understand the classical world, you had to see it as the shadow of the quantum one, a shadow cast by interference. And perhaps that's what it feels like. The tangible world around us is that shadow, the outline left after the infinite dance of possibilities has folded itself into stillness. We live within that shadow, walking paths that were once 1,000 overlapping threads, now merged into one. So the next time you watch something ordinary, a leaf drifting, a glass tipping, a stone skipping across a pond, imagine the hidden orchestra underneath. Picture every atom trying countless variations of motion, each one contributing its tiny rhythm. All those variations interfering until the chaos melts into one visible outcome. That's what it means for the classical world to be reborn from quantum chaos. It's not a transition from small to large or from strange to normal. It's the same song, heard from farther away. Up close, the sound is wild and complex. From a distance, it becomes melody, and in that melody, we find peace. The world is not fighting its uncertainty, it's composing with it. Out of infinite potential, it writes the one story that can be told without contradiction. Out of quantum noise, it makes silence. Out of silence, it makes everything. From here, our quiet exploration turns towards something small. So small it can barely be imagined, yet so important that without it, there would be no difference between the whispering quantum world and the calm, predictable one we live in. This tiny constant, this measure of the universe's subtlety, is known as h-bar, the shortened name for Planck's constant divided by 2 times pi. But numbers and symbols don't really capture it. Think of it instead as the width of nature's brushstroke, the smallest unit of rhythm with which the universe paints reality. In a way, h-bar is like the boundary between dreams and decisions. It tells us how much the world is allowed to shimmer with possibility before it must settle into something definite. Without it, everything, particles, light, even you, would behave as an infinite wave, spreading everywhere, never resolving. With it, the universe gains texture. Possibility condenses into patterns and patterns into form. It's a constant that doesn't just measure action, it defines what action even means. To feel its importance, imagine standing at the edge of a vast lake on a windless morning. The water's surface looks perfectly still, but when you lean closer, you see the faintest ripples, tiny tremors spreading outward from invisible disturbances beneath. Those ripples are the signature of h-bar. They represent how finely the universe allows motion to fluctuate before calm returns. The smaller the constant, the tinier the ripples, and in our universe, h-bar is unimaginably small. It's so small that on human scales, the ripples have flattened entirely. But they're still there, hidden beneath the stillness, shaping everything we know. The effect of this constant is subtle, but profound. For the tiniest particles, electrons, photons, atoms, the value of h-bar is just right to make their wave nature impossible to ignore. They spread, overlap and interfere with one another like musical notes played in an echoing chamber. The world of the very small is fluid because h-bar gives it room to dance. But for large objects, like a grain of dust or a person, the constant is so tiny compared to their total action that the interference fades away. Their quantum ripples shrink to invisibility. The orchestra that once played infinite melodies now hums in unison, producing the steady rhythm of classical reality. This is why, when you drop a ball, it falls predictably, rather than shimmering through every possible trajectory. The h-bar of the universe is too small to let macroscopic uncertainty survive. Only when things become tiny, so small that their total energy and motion are measured in whispers rather than shouts, does the quantum rhythm begin to show itself again. You might think of h-bar as a kind of cosmic volume knob. Turn it up, and the universe grows noisier, richer in interference and superposition. Turn it down, and the harmonies fade, leaving the clear melody of determinism. If it were larger, quantum effects would invade our daily lives. Coffee cups would hum with uncertainty, chairs would flicker between here and there, and every breath you took would shimmer with probabilities. If it were smaller, the quantum world would shrink into silence, hiding beneath the reach of any experiment. But at the value it has, tiny, but not zero, the universe is balanced perfectly between chaos and calm. Enough shimmer to make life interesting, enough stillness to make life possible. It's strange to think that the size of this constant is what allows our sense of certainty to exist. All of classical mechanics, the smooth, predictable motion of planets, the steady ticking of clocks, the structure of atoms, depends on h-bar being small enough that most of the interference cancels away. It's as if reality holds its breath just long enough for stability to form. The delicate beauty of our world, the orbit of the moon, the swing of a pendulum, the beating of your heart, is built atop the faint whisper of quantum noise, tamed by this constant's tiny value. And yet, in that smallness lies freedom. Because h-bar isn't zero, the universe never becomes entirely rigid. There is always a trace of possibility, a hint of spontaneity woven through existence. Even the most predictable process carries within it a ghost of unpredictability, a vibration that never quite goes away. Every stable atom hums faintly with uncertainty. Every beam of light flickers, not because it's broken, but because it's alive. This is perhaps the most poetic aspect of h-bar. It ensures that perfection in the universe is never frozen. The laws of physics are precise but never absolute. There's always room for variation, for creativity, for emergence. A universe with no h-bar would be silent and lifeless, a marble sculpture that never changes. Our universe, with just enough of this small constant to let the edges blur, is like a song that keeps improvising on its own theme. The tiny number also defines what we can know. In the 1920s, Heisenberg showed that because h-bar is finite, we can never measure both position and momentum, the where and the how fast, of a particle with perfect accuracy. The more precisely we know one, the fuzzier the other becomes. But that's not a failure of our instruments. It's the way reality is written. Nature has chosen fluidity over rigidity, rhythm over perfection. H-bar sets the minimum grain of that rhythm, the smallest possible unit of uncertainty that can exist. If you want a picture of this, think of an artist painting a landscape. Up close, each stroke of colour seems rough and imprecise. Step back, and the image becomes whole. The world's quantum uncertainty works the same way. The brushstrokes are made of H-bar. Up close, things are fuzzy and probabilistic. But from a distance, at our human scale, the details blur together, creating a coherent, stable picture. We live in that coherence, unaware of the brushstrokes that make us. There's a quiet comfort in realizing that certainty and uncertainty are not enemies, they're partners. Without uncertainty, there could be no creativity, no variation, no life. Without certainty, there could be no structure, no memory, no meaning. The universe balances the two perfectly, holding us between the shimmering quantum sea and the solid ground of classical physics. And at the heart of that balance lies this constant, a number too small to see, but large enough to define everything. So whenever you see something steady, a candle flame, a falling leaf, a planet in its orbit, remember that beneath that calm is an ocean of motion, tamed by H-bar. It is the measure of the universe's gentleness, the scale on which possibility becomes reality. It tells us that even the quietest world still hums with invisible song, and that every note, no matter how soft, belongs to the same symphony. As our journey drifts toward the next part of the story, we'll step out of the world of ideas and back into experiments, into ways we can see these invisible harmonies made visible again. Because even though H-bar is small, its presence can be revealed in light, in reflection, and even in the humble patterns of a laser beam striking a foil. The whispers of the quantum world can be made to sing, and in their song, we find proof that the smallest things carry the greatest meaning. The path opens wider, and the pattern deepens. The story now moves from imagination to something you can actually see with your own eyes. Up until now, all these ideas, waves overlapping, paths interfering, actions adding and cancelling, might have felt like a kind of poetry, a whisper about how things might work beneath the surface. But in the right light, that whisper becomes visible. Quantum interference isn't just theory, it leaves traces, tiny patterns of brightness and darkness that speak directly from the subatomic world. And if you know where to look, even a small beam of light can show you the footprints of all those invisible paths. Imagine a simple experiment, nothing more than a laser pointer, a thin piece of foil with fine stripes etched into it, and a white wall. You dim the lights, turn on the laser, and aim it through the striped foil. The beam hits the foil, passes through the alternating openings, and spreads onto the wall. What appears isn't a single red dot, but a whole row of glowing spots, bright, evenly spaced, like pearls on a string. Between them lie areas of shadow where the light has cancelled itself out. You can see it right there, light interfering with itself, not as an abstract equation but as a visible rhythm. Each bright spot corresponds to one set of paths where the waves of light have met in step, crest upon crest. Each dark gap marks where the waves have arrived out of sync, crest against trough, cancelling perfectly. The pattern is delicate, precise, and strangely alive, proof that even something as familiar as light is still weaving together infinite roots before your eyes. Every photon that leaves the laser could have gone through many openings in the foil, but the pattern that emerges is what happens when all those possibilities interact. Now here's the deeper wonder. If you start covering parts of the foil, say blocking every other stripe, the pattern changes. Some of the bright spots vanish, others grow stronger. By selectively removing paths, you reveal the quiet structure underneath, the hidden contributions that normally cancel. When you block certain paths, you prevent those cancellations, and new interference appears. The wall, that plain patch of white, becomes a kind of window into the invisible arithmetic of nature. If you could slow time and watch a single photon make this journey, you'd never see it split in half or travel two routes at once in any ordinary sense. But if you repeat the experiment one photon at a time patiently for hours, the pattern builds itself again. Each little spark seems random, but collectively the spots form the same rhythmic pattern. It's as though each photon remembers where all the others might have gone. The pattern doesn't belong to any one particle, it belongs to the wave of possibility they all share. This isn't just a parlour trick or a curiosity. It's one of the most direct ways we can glimpse quantum mechanics acting on the macroscopic world. Those alternating bands of light and dark are the universe speaking in interference. Each photon has followed every possible path, carrying with it a tiny spinning phase, a rhythm tied to its action, and all those rhythms combine on the wall. Where they hum together, the light shines bright. Where they clash, darkness blooms. It's easy to look at this and forget how radical it is. The wall in front of you holds the shadow of infinite paths. The pattern is not drawn by a single route, but by every route that could have been. Each bright dot is an agreement between countless possibilities, each dark gap a disagreement so perfect it erases itself. The universe, it seems, doesn't waste even the paths that don't happen. They all contribute to the final image, the balance of brightness and absence, the visible and the void. The beauty of experiments like this is how simple they are. You don't need a particle accelerator or a vacuum chamber. The same principle appears whenever light passes through a fine mesh, or when sound waves overlap in a quiet room. Even the rainbow shimmer of soap, bubbles, or oil on water comes from interference. The same physics written in colour instead of brightness. Every ripple of iridescence you've ever seen is the universe performing its quantum dance in slow motion. And beyond beauty, there's meaning. Feynman used to say that interference is the heart of quantum mechanics. Without it, the quantum world would collapse back into ordinary determinism, a bland repetition of straight lines and single outcomes. Interference is what gives reality its texture. It's what allows the universe to explore possibilities, to compose rather than dictate. The bright spots and shadows are reminders that everything you see is the product of invisible collaboration. Waves meeting, disagreeing, reconciling, until the image of the world takes shape. We can take the idea further. Imagine that instead of light, we used electrons, atoms, or even large molecules. The same pattern appears, faint but unmistakable. Matter interferes with itself, just as light does. The difference is scale, not principle. Each electron carries its own phase, its own tiny arrow spinning with action, and when many such electrons travel through slits or crystals, they create the same kind of pattern on a detector. The interference isn't in the particles themselves, it's in the probabilities, the invisible rhythms that describe them. You might say that reality itself is a kind of interference pattern, built not from light or matter alone, but from the interaction of every possibility that exists. What we call solid, or certain, is the bright fringe, the place where the waves of potential align long enough to be noticed. What we call nothing is the dark fringe, where equally real possibilities cancel one another into silence. Both are necessary. The world depends as much on the paths that cancel as on those that remain. There's something profoundly human in this too. Our own lives form interference patterns of a sort. Choices we make and choices we don't overlap invisibly. Paths we never take still influence the shape of the path we do. Each decision, each hesitation, adds its own phase to the story. Some cancel, others reinforce, and the person we become is the pattern that emerges from all those invisible intersections. As you look again at that glowing pattern on the wall, remember that it's not just light you're seeing, it's time, energy, and possibility entwined. It's the universe revealing how it thinks, how it balances chaos and harmony in the same breath. Every bright spot is a tiny yes, every dark gap a quiet no, and together they form the grammar of existence. And when the experiment ends and you switch off the laser, the pattern fades, but the principle remains. The world continues its infinite calculation, adding and cancelling, weaving interference patterns far beyond our sight. Somewhere, in the hum of atoms and the shimmer of starlight, that same rhythm continues. Quiet, perfect, endless. As we drift further into this story, we'll begin to see that interference doesn't just create pretty patterns on walls. It shapes the world at every level, from the flow of electricity in your phone to the chemistry that fuels your breath. It's the quiet work of quantum mechanics everywhere, the invisible conversation that holds matter together. Even the simplest things we take for granted exist only because the universe is, at heart, an orchestra of overlapping waves, all finding their harmony. If we follow the light from that glowing wall a little further, its meaning begins to spread. The interference pattern isn't only a laboratory curiosity or a poetic idea. It's the foundation of almost everything that happens in the world around you, even the parts that seem solid and ordinary. Once you begin to recognize it, you start to see interference everywhere. In every breath you take, every color you see, every spark that flickers through the circuits of your phone. The whole universe hums with overlapping possibilities, and out of that quiet hum, the visible world takes shape. Let's start with something familiar. Color. The deep blue of the sky, the bright shimmer of a beetle's wing, the shifting hues of oil on a puddle after rain. All of these come from interference. Light waves of different rhythms bounce, overlap, and cancel, allowing only certain tones to survive. The blue you see overhead is not a pigment painted across the air, but a symphony of scattering and interference between countless photons and air molecules. Each molecule nudges the light a little, changing its path and rhythm, and together they weave the colour of the sky. The same happens in butterfly wings or peacock feathers. The colour isn't really there. It's created by layers so fine that they coax like waves into harmony. You are not seeing a surface. You are seeing an interference pattern that nature has built into beauty. Now think of something closer to your hand, your phone or your laptop. Inside, tiny rivers of electrons flow through a lattice of atoms. Those electrons too are waves. They don't slide down little metallic tunnels like beads through straws. Instead, they ripple through a forest of quantum possibilities, meeting obstacles, splitting, recombining, cancelling and reinforcing. Every transistor, every logic gate, every pixel on your screen depends on those interference effects. The circuits only work because the electrons are waves, because their probabilities interfere. If you ever wondered how your device knows when to switch on or off, the answer, in a very real sense, is it listens to the music of quantum interference and responds to its rhythm. Even life itself owes its efficiency to these same principles. Deep within the cells of a leaf, in the green machinery of photosynthesis, light energy is captured and converted into the chemistry of life. Scientists once thought that the process must be wasteful, that energy would scatter before it reached its destination. But when they looked closer, they found something astonishing. The energy from each photon doesn't take one path. It travels through multiple routes within the molecule simultaneously, exploring all of them in parallel. Then, through quantum interference, only the most efficient route survives, the one that delivers the energy perfectly to where it's needed. Plants, it seems, learned to trust quantum mechanics long before we did. Even the warmth of your own body, the way your muscles move and your thoughts form, depends on interference at the smallest scales. Chemical bonds, the links that hold atoms together, exist only because electrons occupy standing wave patterns around nuclei. These standing waves are quantum harmonies, the places where the destructive interference of impossible states leaves behind something stable, Without them, matter wouldn't hold. Your breath, your skin, your heartbeat are all woven from cancellations and resonances, trillions upon trillions of them, repeating every instant. And if you zoom out past the human scale, the same story continues. The stars in the night sky shine because of nuclear fusion, and that process depends on quantum tunneling, another kind of interference. In the heart of a star, protons push against each other, repelling with all their might. By classical reasoning, they should never collide, never fuse. But the quantum world doesn't accept that finality. The wave describing one proton overlaps slightly with the wave describing another, and where those waves meet, there's a faint, ghostly chance that they'll interfere just right, allowing the particles to appear momentarily together, close enough to fuse. Every twinkle in the sky is born from that improbable interference, from the overlap of possibilities that the universe quietly allows. It's humbling to think that the same principle, shaping a simple pattern of light on a wall, is also responsible for the birth of stars, the colour of butterflies, and the electricity that powers thought. Interference is not a side effect. It's the core mechanism of reality's creativity. Without it, energy couldn't flow efficiently, matter couldn't cohere, and life couldn't exist. The world would be a collection of disconnected events, each isolated and dumb. Interference is how the universe learns to communicate with itself. You can feel it in more familiar everyday ways too. Think of sound. When two musical notes meet, they can blend beautifully or clash painfully, depending on how their rhythms line up. When they align perfectly, the sound swells into harmony. When they don't, the air between them goes still. The same thing happens at every level of existence, from the tiniest electron wave to the grandest cosmic vibration. The universe is constantly testing combinations, letting some fade and others flourish. What remains is always the simplest, most resonant outcome, the one that keeps the whole composition coherent. It's strange how much comfort this offers. We often think of the world as a place of struggle, of particles colliding, forces opposing, systems battling for equilibrium. But beneath that surface, there's a quiet negotiation happening all the time. The quantum world isn't at war with itself, it's constantly finding balance through interference. The collisions, the frictions, the apparent oppositions are part of a deeper harmony. You too are made of that harmony. Every breath you take is interference embodied. Air, molecules colliding and cancelling, vibrations finding equilibrium in your lungs. The hum you sometimes hear when the world is silent, that faint ring in your ears, is a reminder that you're part of the same vast orchestra. And if you could listen beyond hearing, if you could slow down your perception until every vibration became audible, you might notice that the world around you never stops singing. The hum of electronics, the colour of sunlight through leaves, the pulse of blood beneath your skin, all are harmonies of waves interfering, choosing and refining. The quiet work of interference is the universe's way of composing itself anew every moment. So perhaps, when you think of quantum mechanics, don't picture equations on a chalkboard or particles darting in empty space. Picture patterns, waves meeting waves, sometimes amplifying, sometimes cancelling, always composing. The beauty of the world isn't built from things, but from relationships, from how every note interacts with every other. What you see, hear, and touch are the bright spots of that pattern, the parts that sang loud enough to last. As we drift toward the next step of our journey, we'll explore what happens when that harmony starts to fade. When the quiet interference of the quantum world meets the noise of the macroscopic one. What happens when those delicate rhythms lose their alignment? When coherence gives way to chaos? Strangely enough, that's when the single solid world we know emerges, the moment when infinite possibilities blur into one. If we follow the music of interference a little further, the melody begins to change. The bright harmonies that once shimmered between endless possibilities start to fade, replaced by a softer, singular tone. the sound of the world as we know it. What was once a symphony of quantum rhythms slowly becomes one quiet note, reality. It isn't that the other notes are gone, they've simply drifted out of sync, dissolving into a mist of unhearable whispers. This, in gentle terms, is what physicists call decoherence. At its heart, decoherence is what happens when the delicate rhythm of quantum waves meets the noisy world around it. A particle, on its own, can exist in superposition, overlapping possibilities, like an orchestra of paths all playing together. But the moment it touches its environment, a photon of a light, a molecule of air, even the wall of the container holding it, its rhythm begins to falter. Each interaction adds a tiny vibration, a tiny disturbance. The once perfect harmony of quantum phases slips, scattering into chaos. The orchestra is still there, but it's out of tune. The overlapping melodies blur into a single steady hum, what we perceive as one solid, definite outcome. You might imagine this through sound. Picture a choir singing softly in an empty cathedral. Every voice resonates perfectly, filling the air with echoes that overlap and amplify each other. That's coherence, the unity of the quantum world. Now imagine someone slowly opening the doors to the street outside. The hum of traffic seeps in, footsteps echo, wind stirs the air. The voices no longer blend so cleanly. Their harmony unravels until only a dull, single tone remains audible. The song hasn't been silenced, it has merged with the environment, its details lost in the larger soundscape. That is decoherence, not a collapse, but a blending. In the early days of quantum theory, scientists struggled to understand why we never see superpositions in daily life. Why don't we see a ball existing in two places at once, or a cat both asleep and awake? The equations seem to allow it, but nature, somehow, always resolved those strange dualities into a single visible state. Decoherence offered the answer. When a quantum system becomes entangled with its surroundings, even slightly, its internal harmony scatters. The infinite possibilities remain in theory, but their rhythms are now hopelessly out of sync. They no longer interfere, they no longer compose a visible pattern. What remains is the one consistent thread, the outcome that survives the noise. It helps to picture this as fog. Imagine a mountain path on a clear morning, every rock and branch sharp in the light. That's coherence, the crisp outline of quantum possibilities, perfectly defined. But as the air thickens and the fog rolls in, the details fade. The path doesn't disappear, it simply blurs. The infinite routes the traveller could take all merge into one faint trail, visible through the mist. The world becomes quiet, familiar, predictable. The quantum becomes classical. This is why we never notice quantum strangeness in our everyday experience. Everything around us, the air, the light, the warmth of the room, constantly interacts with everything else. Every atom in your body is in conversation with billions of others through vibration, heat, and touch. The environment acts as an ever-present audience, and its applause, so to speak, drowns out the subtleties of the performance. By the time those quantum harmonies reach our scale, they've long since faded into a single, stable tune. And yet, that doesn't mean the underlying music is gone. It still plays endlessly underneath the noise of the world. The difference between the microscopic and macroscopic isn't a matter of different laws, it's a matter of rhythm. In the quiet spaces where particles can stay isolated, in the vacuum of space, or in carefully shielded laboratories, coherence can be preserved for fleeting moments. Scientists have trapped atoms and even tiny molecules in such stillness that they behave like pure quantum waves again. For an instant they sing in full harmony with themselves, but as soon as they touch the noisy outside world, their song melts back into silence. If the universe were entirely isolated, no heat, No sound, no other matter to disturb it. The quantum music would play forever. But we live in a universe of interaction. Everything touches everything else. Every atom carries echoes of every other. The environment doesn't destroy possibility, it weaves it into the tapestry of reality. Decoherence is that weaving, the process by which the infinite becomes the particular. There's something deeply human about this idea. We too live in superposition of thoughts, feelings, choices not yet made. But as we act, as we connect with the world and each other, those possibilities condense. They become decisions, moments, memories. The collapse isn't an ending, it's simply the point where our internal symphony joins the larger song of the world. The future still holds infinite melodies, but in the present, we can only live one of them at a time. It's worth noting that decoherence doesn't violate the magic of quantum mechanics. It doesn't destroy the other possibilities, it only hides them. Each potential outcome becomes entangled with a different version of the environment, a different rhythm, a different phase of the whole. What we call reality is simply the melody that remains audible in the sea of infinite sound. If we could somehow listen to the entire composition, every note, every interference, we might realize that all the possibilities still exist, overlapping beyond perception, perfectly consistent in their own layers of resonance. To describe it mathematically, physicists talk about a density matrix, a structure that keeps track of all the possible states of a system. But when you trace out the environment, when you average over all the noise, the interference terms fade away, leaving only the classical probabilities we experience. In plain words, once the orchestra becomes too large and the echoes too tangled, the harmony can no longer be heard distinctly. We hear only the loudest note. That note is what we call the real world. There's a quiet comfort in that. Decoherence doesn't mean the universe is losing something. It means that everything is finding its place in the larger rhythm. The paths don't vanish. They blend. The possibilities don't die. They mature into the steady hum of existence. Even the silence that follows is part of the song. So when you look around your room, the lamp glowing, the shadow on the wall, the air trembling slightly with your breath, remember that all of it was once quantum, vibrating with infinite potential. The reason it feels solid, familiar, predictable, is because the possibilities have all fallen into step. The orchestra of the universe has found its tempo, and you are living within its rhythm. As we drift into the next part of our journey, we'll see how physicists describe this dance of balance with something deceptively simple, a kind of recipe that tells space and time how to move in harmony. It's called the Lagrangian, and from it, every law of nature can unfold, like a verse in a song. As our quiet journey drifts onward, the fog of decoherence begins to settle, and what emerges from it is not chaos, but order, a pattern so elegant it feels almost alive. The universe, it seems, doesn't just behave, it composes, and beneath all the noise there is still a kind of notation guiding the melody. In the language of physics, that notation is written in something called the Lagrangian. The word itself sounds technical, almost intimidating, but the idea behind it is gentle and deeply human. A Lagrangian is simply a recipe, a set of instructions for how motion unfolds in the most balanced possible way. It tells space and time how to move gracefully together, how to exchange energy without waste, how to keep the dance of the cosmos in perfect rhythm. Once you know the right recipe, everything else follows. Gravity, electromagnetism, the gentle pulse of light, even the waves of probability that shape the quantum world. All of them can be written as variations on this same simple theme. To see what it means, imagine a musician preparing to play a song. Before they strike a note, they know the structure, the tempo, the rhythm, the key. These aren't the music itself, they are the rules that guide it. The Lagrangian is like that. It doesn't describe one thing, It defines how all things should move when they are free to express themselves. Every law of motion, every ripple of matter or field can be derived from it. It is nature's sheet music. When Feynman looked at the universe through his sum over histories, he realized that the Lagrangian sits at the heart of it all. Every path the particle could take carries a rhythm determined by this simple quantity, how its energy of motion compares to its energy of position, and how those change with time. In the older mathematical language, we might say the action is built by summing the difference between these two forms of energy along the particle's journey. But spoken softly, it means this: each path keeps a diary of how much of its journey was spent moving and how much was spent waiting. The Lagrangian is that diary's single line of poetry, the line that captures the balance of everything that happens in between. And the miracle is that if you write down the correct Lagrangian, the entire story of nature unfolds automatically. The principle of least action ensures that out of all possible motions, the real one is the one that makes this quantity, the action, stay steady, balanced, and quiet. Like a violinist finding the pitch where the note rings true, the universe always tunes itself to this point of harmony. It's worth pausing to feel the humility of that. Every grand equation of physics, from Newton's falling apple to Einstein's curved space-time, can be derived by asking one question: what is the simplest, most harmonious way for the universe to move, given this recipe? The difference between mechanics, electromagnetism, and gravity isn't in the mathematics, it's in the ingredients. Change the recipe and you change the world. But the principle, the search for balance, remains the same. This view turns physics from a catalogue of forces into a kind of art form. Instead of asking what pushes this or what pulls that, the Lagrangian approach asks what melody is being played here. It's not about separate causes and effects, but about the elegance of motion, the way energy transforms from one form to another without ever being lost. It suggests that nature doesn't act out of command or compulsion, but out of grace. If you've ever watched a bird gliding effortlessly on an updraft, or a planet circling quietly through the dark, you've seen the Lagrangian at work. The bird doesn't flap wastefully, the planet doesn't wander. Each follows the path that keeps effort minimal and flow continuous. This is the essence of least action, motion that feels inevitable because it is the only motion that doesn't struggle against itself. We can even think of this as a kind of empathy built into the universe. Everything responds not to rigid rules, but to what's best for the whole. When you write a Lagrangian, you're not dictating how one particle moves. You're describing how all of space and time cooperate to let motion happen. It's a law of relationship, not command. There's a deep beauty in the fact that this same logic applies to everything. The equations that govern electromagnetic fields, for example, come from a Lagrangian that describes how light prefers to move freely, spreading its energy evenly in all directions. The equations that define gravity arise when you write a recipe that tells spacetime itself to curve gently around energy, rather than break or snap. Even the strange interactions of quantum fields, where particles appear, vanish, and reappear like notes in a dream, can be understood as the universe following its own principle of balance. This approach has become so universal that physicists now use it as their compass. When a new force or particle is discovered, they ask not what it does, but what its Lagrangian must be. What recipe could produce that particular flavour of behaviour? In a sense, all of modern physics has become an act of listening, trying to hear the faint melody that the universe plays and then writing it down in mathematical form. But even if we set aside the equations, the idea behind the Lagrangian speaks to something timeless. It suggests that balance is not an accident, it's the fundamental pattern of existence. The same principle that governs a photon's path governs the arc of your hand as you pour water into a cup. Both follow the route that conserves energy, that minimizes unnecessary motion. Even our own choices sometimes echo this principle. We seek equilibrium, harmony, efficiency, not out of calculation but out of instinct. We move unconsciously in the way that feels most natural, and in doing so we mirror the cosmos. Perhaps that's why this principle feels so peaceful. It reassures us that the universe doesn't need constant correction or intervention to stay in order. Everything, from the spin of an electron to the drift of galaxies, already contains its own sense of balance. The Lagrangian is the written record of that balance, the cosmic score that every motion follows, no matter how grand or small. So when you look at the night sky, imagine not a collection of separate forces battling for dominance, but a choreography, every star, planet and photon moving in rhythm, guided by the same quiet rule. The universe is not an argument of energies, but a composition of them, and that composition, as strange and complex as it seems, can be summarized in one sentence. Nature always takes the path of greatest grace. As we drift now into the final part of our journey, the focus will widen. We'll leave the equations behind and listen for the poetry they suggest. From the lifeguard's sprint across the sand to the photon's quiet journey through glass, every story we've told is part of the same symphony. The last chapters of our voyage will explore that unity, how the physics of motion becomes the philosophy of being, and how behind every motion there is stillness waiting to be heard. If we follow the rhythm of the story a little further, something remarkable begins to emerge. After all the equations and experiments, the lasers and lifeguards, the spinning arrows and whispering constants, we arrive at something that sounds less like physics and more like music. Everything that moves, every photon, every atom, every breath, is part of one continuous symphony. Each note follows its own path, yet all belong to the same composition. The principle of least action, Fermat's fastest light, Feynman's infinite paths, they're not just mathematical tricks, they're nature's way of keeping time. You can trace this melody all the way back to that lifeguard on the beach, sprinting over sand and diving into water. She doesn't know it, but she's playing her part in this cosmic orchestra. Her path, curved gently toward the swimmer, mirrors the way light bends as it passes from air into water, each taking the route of least delay, the rhythm of most grace. Fermat's insight centuries ago wasn't only about geometry, it was about harmony, the realization that even something as intangible as light seems to act as though it knows how to stay in tune with itself. Then came the thinkers who took that simple truth and built upon it. From Maupertuis and Hamilton to Feynman pacing in his Princeton office, each one added a new instrument to the ensemble. They discovered that this principle of balance, the universe's insistence on elegance, appears everywhere. Whether it's a falling apple or a particle exploring infinite routes, the same music is playing. Nature doesn't calculate every outcome, it resonates. Think about the way a violin string behaves when you touch it lightly at its midpoint. It doesn't stop vibrating, it reorganizes. The single wave splits into halves, then thirds, then fifths, each part resonating with the others to form harmony. The string is finding its natural frequencies, the points of least resistance where motion flows freely. The universe works the same way. Every event, every particle, every interaction is a vibration searching for its place in the larger resonance. This is why the world feels coherent even though it's made of countless tiny uncertainties. The things we experience as solid, rocks, rivers, stars, are just stable chords in an infinite composition. Their stability comes from repetition, from resonance. The quantum ripples beneath them hum together so perfectly that, to us, they seem still. Every stable structure, every enduring form is a long note held in the cosmic song. There's something deeply comforting in this. It tells us that the universe isn't a machine grinding through commands. It's more like a choir, each voice adjusting slightly until harmony is found. The reason equations can describe it so beautifully is that equations are, in a sense, the written form of that music, the score by which the cosmos performs. The principle of least action, which might once have sounded abstract, is just the notation for balance. When energy and time trade places in perfect rhythm, the result is what we call a law of nature. And when you start to see it that way, everything becomes part of the same language. The orbit of a planet, the reflection of light, the flutter of a leaf in the wind all follow the same quiet rule. Each chooses unconsciously the path that wastes nothing, that keeps motion smooth. In the language of physics, we say these are the stationary paths, the ones where the action stays constant. In softer words, they're the movements that feel inevitable because they are in perfect tune with their surroundings. This is why beauty and truth so often overlap in science. A beautiful theory, one that feels graceful, tends to be correct. It's not superstition, it's resonance. The same patterns that make a melody pleasing to the ear make the universe consistent to the mind. The rhythm of a pendulum, the spiral of a galaxy, the symmetry of an atom, all express the same aesthetic. Simplicity within complexity, order within motion. Perhaps that's what Einstein meant when he said that the most incomprehensible thing about the universe is that it's comprehensible. The fact that we can write its rules in the language of balance and action isn't a coincidence, it's an invitation. We're not outsiders watching the symphony from the balcony. We're instruments within it. Our minds, our senses, our curiosity, they're all ways the universe listens to its own song. You can sense that music even in silence. Watch sunlight, reflected on a pond. Each ripple bends and stretches the light, creating shifting patterns that never quite repeat. The same principle that guided Feynman's particle is alive there, glinting in every flicker. Or listen to the soft rustle of leaves in a breeze. Air currents twist and cancel, just like wave functions do. What reaches your ear is not the chaos of movement, but the remainder of countless cancellations, the audible melody of interference made large. It's easy to forget that when we talk about laws of motion, we're really talking about poetry that happens to be measurable. Newton, Fermat, Feynman, they were all trying to describe the same thing in different dialects, the grace with which nature moves. Each law is just one stanza in a much longer piece, one that began long before humanity and will continue long after. If you've ever felt a moment of inexplicable stillness, a second where everything seems perfectly placed, perfectly timed, that's the same balance you've been hearing about. It's the same phenomenon that keeps the planets circling, the photons travelling, the atoms vibrating. It's not mystical. It's simply the deep satisfaction of living in resonance with the world that built you. And maybe that's the real meaning of Feynman's insight. When he said that a particle explores every path, he wasn't only describing physics, he was describing us. Each life, like each particle, moves through an ocean of possibilities, and what becomes real is the path that harmonizes best with the rest of the world. We too are part of the grand interference pattern, waves of intention, memory and chance combining until a single melody emerges, the life we're living. The lifeguard sprint, the beam of light, the path of a falling leaf, they're all different verses of the same refrain. Each follows the principle of least action, each seeks balance, and together they form the symphony of everything moving. Nature isn't calculating its way forward, it's resonating, finding rhythm within chaos. As we drift onward, our exploration will turn inward once more, to the question of why the world feels solid when it's built from something so fluid, and why certainty feels so comforting when it's born from uncertainty itself. We'll discover that what we call reality is the melody that remains after all the tuning, the quiet after the orchestra finds its key. And perhaps we'll find that what feels like stillness is, in truth, the universe still singing. If we drift deeper into this quiet harmony, a curious thought begins to surface. We live in a world that feels solid, definite, and continuous. When you touch the surface of a table, it doesn't shimmer with uncertainty. When you drop a pebble into a pond, it follows one clear arc through the air. Everything seems concrete, unwavering, stable. Yet beneath that calm, beneath every grain of matter and flicker of light, the universe is still humming its quantum tune, a vibration of countless overlapping possibilities. The solidity you feel is not the absence of chaos, it's the average of it, the final melody after the tuning ends. Think of an orchestra again, just before a concert begins. Each musician tunes their instrument, strings humming, brass warming up, woodwinds fluttering through scales. It's noisy, unpredictable, a swirl of sound with no centre. But then, the conductor lifts a hand. The noise fades, the instruments align. The moment the first note is played, you hear only harmony, not because the chaos vanished, but because it resolved into something coherent. That's how reality works. The quantum world beneath you never stops tuning itself. What you experience as a single, definite reality is the symphony finally playing in key. The same principle can be seen in every aspect of our existence. Take your own senses, for example. The image of the world that reaches your eyes is not raw reality. It's a carefully filtered harmony. The photons entering your pupils bounce and scatter off millions of atoms, each with its own quantum uncertainty. By the time they reach your retina, they've been averaged, smoothed, turned into coherent light. Your brain then adds another layer of harmony. It fills in gaps, adjusts brightness, invents continuity. You never see the quantum flicker. You see the melody it produces. It's the same with touch. The firmness of a chair, the smoothness of a pebble, the pressure of a key beneath your finger. None of it comes from solid matter in the way we imagine. Matter at the atomic level is mostly empty space. The sensation of solidity arises from electromagnetic fields overlapping, repelling, interfering until they reach equilibrium. What feels like resistance is the music of countless electrons refusing to occupy the same space. The world's smallest orchestra maintaining perfect pitch. Even temperature, the warmth of sunlight on your skin, is interference at scale. The jostling of molecules, billions of tiny vibrations, averages out into the smooth feeling of heat. When you say something feels warm, you're describing the harmony of motion beneath the surface, translated into the language of nerves. Every sensation you have is interference transformed into experience. In a sense, you could say that reality is edited before it reaches you. The quantum orchestra plays all its possibilities, but by the time those vibrations ripple upward to human scale, the dissonance has faded. What remains is the melody of coherence, the version of the universe that's stable enough to live inside. Feynman once said that nature's laws are simple, not because the world is simple, but because the world hides its complexity beautifully. Thankfully, reality edits itself before presenting the final cut. It's not that the deeper quantum chaos disappears, it's just that we can't hear it anymore, like the overtone frequencies of a bell that fade into inaudibility after the first chime. The wilder vibrations of the quantum world die away in our perception. The silence you experience is filled with unending motion. You're always standing in the middle of a storm of probabilities, but the storm is too well tuned to feel. And yet this illusion of solidity isn't deception, it's grace. The classical world exists precisely because the quantum one is so rich. If every molecule around you stayed isolated and coherent, the world would flicker in and out of countless states, never forming a stable image. You couldn't walk, breathe, or think, because everything would behave like that pattern of light in the double-slit experiment. All interference, no definition. What we call reality is the point where interference settles, where decoherence has blurred the possibilities into one visible frame. There's a strange comfort in realizing that what we perceive as ordinary is actually the most extraordinary balance imaginable. The universe hides its chaos behind a curtain of coherence, giving us a world we can touch, name, and live within. It's as if the cosmos itself is performing for us, not pretending, but refining. We are the audience to the final performance, unaware of the endless rehearsals that happen beneath. You can picture it as a dancer gliding effortlessly across a stage. Every movement looks smooth and inevitable, but behind that grace are hours of invisible practice. Small corrections, tiny missteps, each one adjusted until perfection emerges. The quantum world is that rehearsal. The classical world is the dance. What feels solid is the choreography, the result of infinite trial and interference, captured in motion so fluid we no longer see the effort behind it. In truth, the universe never truly chooses one outcome over another. It simply allows time and interaction to blur the edges until the picture becomes sharp. You could say that we don't live in a single reality. We live in the version that coherence permits us to perceive. The rest are still there, humming faintly below the threshold, just as overtones linger in a struck note. We feel the primary tone, but the harmonics remain, subtle yet indispensable. And this brings a kind of peace. If everything solid is born of uncertainty, then uncertainty isn't something to fear. It's the foundation that makes clarity possible. Certainty is just uncertainty averaged across scales large enough to feel calm. The table beneath your hand, the walls around you, the stars above, all are frozen waves, interference patterns stabilized by time. The stillness of the world is an illusion produced by motion so constant it has forgotten how to change. Reality, then, is not the absence of ambiguity. It's the quiet agreement of all the ambiguities underneath. When particles lose their rhythm, when possibilities blur, the world doesn't fall apart. It becomes visible. The fog thickens, and we find ourselves inside it, calling it home. So the next time you rest your hand on something solid, remember that what you're feeling isn't firmness, but harmony. Beneath that touch, countless interactions are taking place, merging and cancelling, making existence smooth. The world is still vibrating. It always will be. We just live in the measure where its rhythm becomes a lullaby. As we drift further into this melody, our focus will shift from what we see to what we imagine, to the possibilities that never made it into the final harmony, but still echo quietly in the background. The universe, after all, is full of choices never taken, paths never walked, and songs that play only in silence. And somehow, all of them contribute to the one we hear. If we follow the harmony of the story a little further, it becomes harder to tell where science ends and poetry begins. Because what the equations have been whispering all along is that the universe is, at its heart, a storyteller. Every moment that passes, every flicker of light, every leaf that falls, every breath drawn, is the visible line of a tale that could have gone countless other ways. And yet, somehow out of all those possible paths, only one thread becomes the world you live in. The rest fade quietly, like echoes of words never spoken. But they were there. They mattered. Every possibility, even the ones you never see, shapes the pattern that remains. The world we call real is not made by erasing the others. It's made by their interference, by their silent agreement to cancel and reinforce until a single version stands clear. The laws of motion, the beauty of least action, the emergence of classical order, all of it is the universe narrowing its infinite imagination into something it can actually say. Imagine, for a moment, walking through a forest in autumn. Leaves rustle around your feet, each one taking a slightly different path to the ground. No two falls are the same. Some spin lazily, some dive sharply, some are caught by a current of air and lifted briefly back upward. You can only follow one with your eyes at a time, but the forest is filled with them. Thousands of possibilities, each completing its own quiet descent. That's what the universe is doing constantly. Every atom, every photon, every wave of energy explores all routes at once. But we, standing here in the forest of possibilities, see only the one that lands near us. It's tempting to imagine that the other routes simply don't exist, that they disappear when they're not chosen. But quantum mechanics doesn't speak in absolutes. It whispers that the unchosen paths are still woven into the fabric of things, that they continue to influence the rhythm of what we do see. Every moment you experience, the light glancing off a window, the breath of air against your skin, is shaped not only by what happened, but by everything that might have. Even our own lives seem to follow this quiet rule. Every decision we make sends ripples through a sea of possibilities. The road not taken doesn't vanish. It remains as a faint pattern, influencing the paths we do walk. The person you could have been, the conversation you might have had, the door you almost opened. All of these invisible versions still play their part in the interference that makes you who you are. The physics that guides electrons and photons also hums softly beneath the patterns of thought and chance. Feynman once said that when a particle moves from one place to another, it tries every possible route, and that the one we observe is the result of all those attempts combining. You can picture that without symbols, without equations. Imagine each path as a thread, shimmering with a colour that represents its rhythm. Some threads glow bright, some fade into shadow, some twist and tangle, crossing one another endlessly. The universe is this tapestry, woven from every thread that could be. The picture you see, the life you live, is just one view of the fabric. The rest remains hidden, not because it's gone, but because the weave is too fine for our eyes. You might even say that time itself is the act of the universe telling one version of its story. Each moment it explores every continuation it can imagine, and through interference one sequence of events emerges. But the unchosen moments still exist in potential, like verses of a poem that remain unwritten, but still affect the rhythm of the lines that do. The present is simply the one the universe happened to recite aloud. This gives new meaning to the idea of the path of least action. It's not that the universe prefers simplicity for its own sake, it's that when every possibility is allowed to speak, the only story that can survive is the one that's most self-consistent, the one where the interference patterns align perfectly, where contradictions cancel and clarity remains. In that sense, what we call reality is the most coherent version of infinity. There's a kind of quiet hope in that thought. It means that the world is not random. It's deliberate, though not predetermined. It's a song composed from countless overlapping voices, each one necessary, even if unheard. The parts we see are simply the harmonies that survive the noise. The rest are the silence that makes the song possible. If you think back to the lifeguard on the beach, you can almost see it again. She could have run faster, slower, entered the water sooner or later, turned her angle by 1 degree. There are infinite ways she might have reached the swimmer, but in the real world, we see only one. That single, graceful curve in the sand isn't arbitrary. It's the survivor of all those possibilities, the path whose rhythm harmonized best with the laws of nature. Every other route still existed for a heartbeat, contributing to the interference that defined the final motion. The same is true for you in every decision you make. Your life too is the visible path that remains after a million other lives cancel and reinforce beneath it. And if we expand that view, the entire cosmos becomes a story of choices never taken. Galaxies collided that might have passed untouched. Stars exploded that might have dimmed quietly instead. Planets formed, others didn't. And yet all those near misses and possibilities form the background that makes this universe, the one you're breathing in right now, possible. It's not the only story that could have been told, but it's the one that harmonized into coherence. You could say that the universe is a storyteller with infinite drafts, rewriting its lines through interference until one version flows smoothly from beginning to end. But it's not a conscious process. It's the nature of being itself. Physics, in its quiet precision, is simply the grammar of existence. The words are matter and energy. The rhythm is time. The meaning, perhaps, is harmony. And in that harmony lies something very close to peace. The unchosen paths don't haunt us. They hold us steady. They make the one we're on possible. Every photon that reaches your eye, every sound that reaches your ear, every heartbeat that finds its rhythm, all of it is supported by the unseen alternatives that never made it to the surface. The world we live in is a collaboration between the actual and the possible, between being and maybe. So as you sit here now, breathing quietly, perhaps you can imagine those invisible threads still shimmering somewhere. Paths untaken, choices unmade, particles that almost travelled another way. The universe holds them gently, allowing them to exist just long enough to make this moment real. The life you're living is one verse in an endless poem, one chord in a timeless composition. The rest of the song is still out there, waiting, humming softly beneath everything. As our journey drifts toward its final chapter, we'll look for the stillness beneath that music, the place where motion itself seems to pause, where every path, chosen and unchosen, comes to rest in a single, quiet understanding. Because in the end, perhaps the most beautiful truth is not how the universe moves, but how it learns to be still. If we follow the story to its quiet conclusion, the pace begins to slow. The symphony that began with vibrations and light, with paths and probabilities, now fades into something deeper, a stillness beneath all motion, a calm that has always been there, holding everything together. After all the complexity, after all the movement, the universe reveals its simplest truth. It acts not by force, but by grace. The physicists who studied least action didn't set out to find poetry. They were looking for rules, for equations that could predict the motion of stars, particles, waves. But what they found, again and again, was balance. The principle of least action is really the principle of effortlessness. The world doesn't waste. Every event unfolds in the way that keeps the total story as smooth as possible, as if the universe prefers elegance over excess. Even chaos follows the path of minimal struggle. If you look at a drop of rain sliding down a window, you can see this principle in a miniature. It hesitates, trembles, then finds a line where the pull of gravity and the stickiness of glass balance perfectly. Once that balance is found, the drop moves easily, almost gracefully. No part of it seems forced. It's the same with light bending through glass, with planets circling the sun, with a pendulum swinging in air. None of these are fights against resistance. They're dances of equilibrium. The universe is always finding the path where tension dissolves into flow. That's what the principle of least action really is, nature's way of keeping itself in tune. Every movement is a negotiation between what could happen and what feels right, between possibility and peace. When you sum over all paths, when you let every potential outcome speak, the one that survives is the one that resonates most quietly with the universe around it. That's the one we see, the one we live in. It's a comforting thought that even the most chaotic things, storms, explosions, the birth of galaxies, are born from this same grace. Beneath their power lies an invisible symmetry, a deep logic of harmony. The Big Bang itself, the most violent event we can imagine, wasn't random. It was the ultimate act of balance. Energy transforming into matter, matter forming structure, structure becoming life. Even creation, at its loudest, followed the quiet rule of least resistance. When we trust quantum mechanics, we trust this deeper order, an order that doesn't need certainty to be complete. In Feynman's universe, every path is allowed, every story told, but through interference and harmony, the chaos resolves. The classical world emerges solid and serene, and beneath it all, that tiny constant Planck's whisper keeps the rhythm steady. What looks like stillness is just the music slowed so much that we can't hear it anymore. Perhaps this is why so many physicists, after a lifetime of equations, end up sounding almost spiritual when they describe their work. They don't mean supernatural, and they mean serene. When you strip away the noise, when you let the mathematics settle into silence, what remains isn't confusion but clarity. It's the realization that the universe doesn't need to force its way forward. It simply allows itself to happen. You can feel this stillness in your own life too if you look closely enough. There's a rhythm underneath every breath, a natural balance between inhale and exhale. Your heart beats in cycles of contraction and release. Your thoughts rise and fall like tides. Even your smallest decisions, when you listen carefully, tend toward equilibrium. We call it intuition, or peace of mind, but perhaps it's the same thing that guides a photon or a planet, the quiet instinct for harmony. When you reach a crossroads and feel, without knowing why, that one path feels lighter than the other, that's the principle of least action speaking through you. Not as a calculation, but as a feeling. Nature doesn't reason its way to efficiency. It feels its way there. Every river finds the easiest route to the sea. Every beam of light finds the fastest path to its destination. Every living thing, consciously or not, moves toward balance. We're not exceptions to that law. We're examples of it. The more you think about it, the more you realize that stillness isn't the opposite of motion. It's what makes motion possible. A dancer can move beautifully only because there's a moment of calm at the center of each turn, a point of balance she keeps returning to. The planets move because gravity and momentum balance perfectly. Even the act of thinking, of understanding, requires quiet between bursts of insight. The world keeps moving not despite stillness, but because of it. This, then, might be the final lesson hidden inside all the mathematics. The principle of least action, the path integral, the sum over histories, they're all ways of describing one truth, that the universe finds peace through motion, and motion through peace. What looks like choice is harmony. What looks like chaos is choreography. What looks like randomness is simply rhythm you can't yet hear. When we accept that, when we stop demanding certainty and start trusting the music, something in us relaxes. The need to know every outcome, to control every motion, fades. We can finally let the world move as it does and see that it's already perfect in its balance. To trust quantum mechanics is to trust uncertainty itself, to understand that not knowing is not ignorance, but participation. The universe is still composing, still refining its melody, and by existing, you are part of that composition. So perhaps tonight, as you lie in the quiet dark, you can imagine the sum of all paths converging, all the photons, atoms, and worlds tracing their possibilities until they settle into stillness. Imagine the infinite interference of the cosmos resolving into one gentle pattern. The room you're in, the breath you're taking, the moment you're living. All of it the calm after creation, the silence after the last note fades. And in that silence you can rest. The universe is still here, humming softly beneath you. The paths have aligned, the equations have balanced. Every wave has found its rhythm and every particle its place. You don't have to solve it or understand it. You only have to listen. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you've already drifted somewhere between waking and dreaming, thank you for joining this quiet journey. If you'd like to wander with me again, you're always welcome. The universe has endless paths to show us and countless melodies yet to play. But for now, let them rest. Let everything rest. You're part of the stillness behind every motion, and that is enough.